Good morning, everybody. Welcome back. And this is our annual ULI review year 2. And we're at our second day of review. And today we're going to cover the research progress on TC3 for fault diagnosis and reachability analysis, as well as on TC4 for integration and testing. So we'll also present the outreach activities in this year and hold a dedicated discussion for the demos in next May. Nara, I see you're turning the camera on. Do you want to say something? Okay, sounds good. So without further ado, let's get started. And Ali, you're the first speaker today. Will you share the screen and take it from there? Ali, you're muted.
Okay. Good morning, everybody. You can hear me now?
Yes, I can hear you. You might want to please make the slides into. Yeah, okay. All good now.
Okay,
thank you.
Perfect. Good morning again. My name is Ali Karimuddini, along with colleague Dr. Yanis Raptis and Melkor Ornik, all together along with the students and postdocs in the team. We are focusing on robust and resilient autonomy for advanced air mobility under TC3, which is runtime fault diagnosis and reachability analysis for in-flight contingency management. So a little bit background about this TC. The goal here is to develop advanced methods for detecting different types of fault and also estimating a reachable region to do kind of on-the-fly mission planning and identifying a feasible and safe reachable sets to replan and kind of as a sort of coming up with a contingency plan here. The challenges, of course, here are faults may happen anytime, anywhere in the system, and we cannot have sensors for sensors on everything, and then we need to understand from the behavior of the system what are the faulty situations that is happening and then react appropriately. But also there is another challenge here. The nature of the systems are the mix of dynamics of the system, whether it is discrete time or discrete event and continuous time, and all of these create a sort of cyber physical systems here that makes it even more challenging to handle the different modes and different failures and different events. To address all these challenges here, we have an approach that has three components. First of all, once we receive the information about the model of the system from TC1, then we're going to be having two approach for fault diagnosis, as you can see on the in the figure on the right side of the image, this slide. So first of all, discrete event system fault diagnosis using a sort of active learning and also considering the uncertainties in the system to detect events that are having a discrete nature, but also continuous fault diagnosis using sampling-based approach that Yanis is working on this problem. So putting all these together, the results of these two blocks is there is a fault. Given that, then we're gonna end up with running a sort of runtime reachability analysis that Melkor is working on it. And the output of this TC will be a fault is occurred, what is the nature of the fault, and what is the feasible region and that can be pursued to maximize the safety. So here are the milestones for our TC. During year one, we were primarily focusing on theoretical developments, active learning, asynchronous and semi-asynchronous diagnosis, developing sampling-based fault diagnosis, and development of theory of guaranteed reachability for systems known to operate on a manifold. So these were the milestones for year one. But in year two, we primarily pushing to more on the software development and verification through different approach, whether it was MATLAB state flow or was on the Guam model or different sort of simulation that is going to be discussed in more detail when we are discussing each of these components. But also at the same time, we continue the theoretical developments on further improving the tools that we were that we had developed during year one. So The team has been very active, 14 publications only in year two. So I'm not including the publication in year one. So just year two, 14 publication. Kudos to the students and postdocs in the team, as well as of course, the colleagues who were mentoring the students to get the job done. So that's here what we have here. Also, another thing that along with other colleagues in other theses, we have been also thinking how we can integrate the effort. This is the proposed integration effort, and we have made the progress, and we hope that we can show some aspect of the work for the spring demonstration. So we have we are working on two prototypes. The first prototype is that working on the mini-hawk, the mini-hawk model, and trying to diagnose the fault. And once we diagnose the fault, we're going to be providing that information to TC1, and they're going to be activating the landing controller. So that's prototype one. And then when it comes to prototype two, not only we diagnose the fault, we hope that we can provide also the reachable goal points that can be utilized by TC1, and we have been closely working with TC4, of course, to know more about the mini-hawk and also integration with other efforts. So thank you to the TC4 folks, and soon we're going to be a start conversation with TC1 team as well. So the conversation here is that the assumptions that we do have here, and we need the support from other TCs, of course, as well, to provide a manageable analytical model for the mini-hawk, for the cruise phase, but also for the landing phase, especially for the reachability analysis. And then hopefully the TC1 can leverage this information and use it as a sort of trigger for landing control of their mini-hawk. So that's the plan that we are working on. So with that, now I'm going to be discussing that. That was an overview of TC3. I'm going to also briefly talk about the discrete event-based fault diagnosis method that we have been pursuing here. A little bit background, what does mean a discrete event system is basically an automata, a set of events and states that are transitioning from one mode to another mode. And the challenge here is that not all events are observable. So in the absence of observability of some of the events, how we can infer from the sequence of events that we can observe, and they are captured by the projection, the natural projection. Basically, natural projection, what does it mean? It means that the observable events and observable behaviors of the system. From observable behavior of the system, can we say what is the type of, if a fault has been occurred, and what is the type of fault, and where that fault has occurred? So we have been focusing on this one primarily on year one, but then what is happening in most existing techniques in the literature, they are assuming that the diagnosis tool that we do have and the system under diagnosis, they are fully synchronized, and we know fully full information about the initial state of the system. That's not always the case, and especially because of the lack of perfect synchronization, that may not be really the case. In replacement of that restriction, we were assuming that, okay, let's assume that there is a little bit uncertainty in the initial state of the system, then we're going to be dealing with sort of the belief states that we have here, and now having the belief state set of initial conditions, then how we can narrow down our estimation of the fault and the state of the system, and that's what we have been focusing on one approach, what is called semi-asynchronous diagnosis, which is just recently published in Expert Systems and Applications. The other work that we have been working is the learning-based fault diagnosis. So what we do here, we follow an active learning approach to inquire about the states and events of the system to complete our understanding of the information with minimum inquiries to the system. So we start forming a sort of what is called OT, or observation tables, and we try to gather information and make our understanding of the system complete, again with minimum inquiries. We go through different checks of closeness, consistency, and then making hypotheses and verifying our hypothesis, and then finally building the diagnoser. So that's a learning-based approach that we have been working on it. So now, in the previous work, the system was assumed to be we do have access to the system, but that's not always the case. Now, what is the situation that we partially know the system? So we have two strategies. First of all, we can assume that we don't know the system, and disregard the information that we have about the system, basically adopting this technology, this method here. Here we assume that we don't know the model of the system. So disregarding the information and assume that the system is unknown and adopt the technique that was presented in the previous slide. The alternative to that is to take advantage of the information that we already have and then build and complete the information for the missing part of the system. So that's what is called partially known DES system. So that's what right now we have completed the results and submitted the results on this one. And if you want to consider one application here, for example, the MCAS system was a situation that we were having partially known information about the system. Part of the system was unknown to the pilot and to the crew system. Then right now we are working to use it as a sort of use case and explain how that technique of partially learning, the learning enabled partially known DES system can be applied here. So the other thing that we are working here is the discrete event systems that we do have. Sometimes the events are having a discrete nature, on-off sort of situation, but sometimes they are having a continuous nature in the sense that they may pass a threshold, and passing that threshold may result in a sort of events, and those thresholds. Identifying those thresholds themselves is a challenge. So what we were focusing is the event detection, especially for those events that are having continuous nature. And then once we identify those events, then we can feed it to our discrete diagnoser. That was another work that we have been doing. So we have been using a sort of, for example, decision tree model to detect different events in our aircraft, the model that we do have, and then once we once we detect those events, then we were using them for our DS diagnoser. Part of this story that we have been working on it is also integrating the actuators, for example, aileron, into the Guam simulator. So you can see that here is the actuator that we have been using, and then the events that are being used here, and here is the DS model of the aileron that you can see here, and two types of faults, whether there is a power outage or jamming, are the two type of faults that we were considering here. And now here you can see one example. How does it look like? The discrete model of the system on the left and the diagnoser on the right. So these two systems are working synchronously. So for example, you can see that now both of them are synchronizing on the initial condition that you can see. And even happens here when the system under diagnosis on the left side, under observation of event A transition to state 2, then on the diagnoser side, you can see that we're going to be transiting to a new state. And that's, of course, there are some uncertainties. There are potentially you're going to be under state 2, 3, or you might be in state 7 or 13, where they might be faulty. So now an unobservable events happen. So the diagnoser does not see that one. So no action is happening on the diagnoser side until the diagnoser see another observable event and you transition back. So continuing this until you're going to get to the state that you're going to be a fault happens, and then you narrow down the faults to a state that right now you can see here that you are either on a state 6 or 7 in system under diagnosis, both of which are faulty. So fault type F1 is happened there. So alternative to this one that was sort of model based, we were assume that you don't have the model of the system, use a sort of neural network approach to build to understand the model of the system and also build a diagnoser. So that's one approach. Or alternatively, without even building the model of the system, directly jump to the to building the diagnoser. So rather than creating an intermediate step to build the model of the system and then build the diagnoser. So both of these approaches we are exploring. So that's a work in progress. But that's would be interesting, especially when we don't have so much information about the model of the system. So as a sort of verification of the system that we have been working, we have been developing simulation platform that integrates the actuator model into the flight behavior of the system. And sorry for the background noise. I'm going to pause here for a second. Okay, so because of the actuator model, integrating the actuator model to the flight dynamics of the system and also the visualization that is happening, the work was presented in a conference, the ICNS last spring. Here is what you can see of the different blocks of the simulator, the actuator, the Guam simulator, and the integration of all these are happening. And here is a visualization of the work. You can see here here is under normal operation of aileron, and at some point we inject jamming. So on the once we inject the jamming, the normal behavior of the system is operating on this state and these two states. So far we are in the normal operation of the system until this point. Oops, sorry. So you see now the jamming is happening. We inject the jamming. So start when it is jamming, it start stalking the head, trying to push it back. So and then our diagnoser, that's the physical interpretation of that one. But our diagnoser is a start circling on the faulty behaviors of the systems and start demonstrating that hey, a fault has happened, and that's the fault that you can consider. So that's a brief overview of this work. Thanks to the students and postdocs in the team, as well as colleagues on the team, both at in CNT and both UIUC team, the group from Dr. Ornick as well, and the NASA ULI program for supporting this effort. I'm going to stop here. If there is any question here, or we can wait until all presentation under TC3, whatever that the time allows. So, any question? I can see the chat box.
Ali, there are a couple of questions from the chat, so you can read the answer from there.
Okay, let me see. I pause it. Are the faults determined from so faults are determined. We do have, there is a question how the faults are determined. There are two types of works that we are doing. One is that we do have the model of the system. The model of the system, for example, here you can see this on the left side. We do have this, we assume that we do have this model of the system. That includes the faulty behaviors of the system and the normal behaviors of the system. And we build our diagnoser and run our diagnoser. So that's one approach that we are doing. And then the other approach is that we don't have that model. So, and then we build it based on our active learning or our neural network model. So both of these methods are considered in our framework. So hopefully, Kevin, I did answer. So at the end of the day, we need this model, whether we have it or we build it. And then there is another question. Iron is asking, are you considering trends per to threshold registering a fault for potential preventive actions? Would your approach accommodate tracking of trends and prognosis? So really, we were working on diagnosis rather than prognostics approach. is primarily we do have so far we do have the model of the system, we do have the faulty behavior of the system modeled, and then we diagnose them. We are working on another framework, which is a sort of adaptivity, add a sort of adaptivity into that, meaning that if new behaviors are added to the system, then we can capture those as well. But for now, I would say the techniques that we do have are primarily right now, we do have the model of the system, the events and faults. No adaptation as far as if new events or new states are added to the system or are removed from the system. So that's something that we are working on it. So that's interesting question, but it's diagnostic. It's not really prognostic at this stage.
Okay, just sorry, Ali, thank you. Just to clarify, forget about the second part, especially the first part. So if you, sometimes the trends may indicate a slowly creeping fault, and potentially there are actions, if you detect that as a warning rather than or caution rather than here it is, here it comes, you may be able to take action at the higher level to prevent that actual fault happening. And so it is still diagnostic, right? But it's almost like you're not waiting for your threshold to be reached and you actually triggering a fault. You may be saying, hey, please keep an eye on this because the behavioral trend is towards a fault. I guess that's more of a germane question here.
Yes, and that's what we refer to as a sort of prognostic, is that even though it is not, the fault has not occurred, but from the trends we can predict and say that a fault might occur based on the trends that is and based on the model that we do have. And given that, but that's we are a sort of, at this stage, it's not kind of proactive approach. We observe the behavior of the system and we interpret it. It's not any sort of prediction that we do have. But that's interesting feedback. We're going to be seeing if we can adopt a sort of more proactive approach and use prognostic framework and adopt it, because we do have the model of the system and we should be able to predict as well. But at this stage, we are observing the events and interpret them.
To add to Irene's question, have you considered maybe using, on the basis of the training data, some more structured approach, AI approach, like the hierarchical hidden Markov model, which would be closer to what Irene is asking, that at a particular higher node, you know that you're getting something faulty down the line. Is that something you've considered?
We are considering a sort of the neural network approach to detect to build a model of the system, to adapt the system, and again is still a sort of not proactive as far as predicting the faults that might occur. But again, I think that's something that we can take a look and see how we can make it a sort of more proactive rather than a sort of reactive.
Yeah, I think it might give you a better chance, this approach. It certainly would not be the 100% prognostic, but it probably would do a bit better because of the structure than the just simple or whatever the neural net you're using, because they are excellent observers, but they can't tell you what's happening next. So especially if there is no model, there is no way that they can tell. Yeah.
Yep. I agree.
Okay, thank you.
Thank you for the comments. And I think there was one more question. If you have time to take it, otherwise I'm gonna follow it up in the chat. I think Kevin is asking.
Are you familiar with CND's cannot duplicates?
Okay. Yes, that's what I was looking. What does CND standing for?
Cannot duplicate.
Okay.
So it's very common, particularly like on F-18, when we land an airplane, faults are tripped through monitors, and then the Navy has to put the aircraft into maintenance, and then all subsequent analyses show nominal behavior. So we get lots of false alarms. And so the whole problem of false alarms, you wouldn't want to have a system that is too sensitive, because then you're replanning. You may cause a trajectory change when it's not needed. And then, okay, and then so the second question there about getting data on these subsystems, linear models don't capture the behavior of these mechanical systems. Typically, like if you, they're not linear. These machines are actually nonlinear systems. Yeah, it's very difficult to get training data. So we've tried to use neural networks for 25 years in modeling subsystems and developing monitors in our aircraft applications. It's proven not to work very robustly. Okay.
I agree, and it's very difficult to get the data, label that data, and interpret that data as a sort of training, and that's sort of all we might end up at the very end is a sort of a proof of concept, which needs a lot of time when it's going to be a scale up for a real aircraft to collect that data and interpret it. So that's I agree that's a challenge when it's going to be practically implemented.
Yeah, I mean, I think in new airplane designs, we'll have data recording capabilities where we can perhaps capture, I'll say, more states of the system where we can do better training and stuff. But right now, this is, I'll just say on legacy aircraft, this is a huge challenge for the industry, is that, CNDs are just very common, and we don't capture the data that's required. Yeah, thank you.
Thank you, Kevin. We'll take a look, especially for this, and see if if there is anything you can or any resources that you can guide us in that would be really helpful.
Yeah, and just to piggyback, this is Mike, to piggyback on Kevin's point.
Sorry, Mike, I have to cut you off.
No worries.
Can you post your question into the chat, and then
Absolutely.
We can continue maybe the discussion in chat or in the discussion session later. Sorry, we have to move on. And next we have Yanis. So Yanis, I see you already have the screen shared, so you can go ahead from there.
Hello, Sang. I hope you can hear me and you can also see my screen.
I can see your screen here.
Thank you.
Maybe
I'm gonna close my camera for bandwidth issues. All right. Okay, folks. I'm Yanis Rapis from North Carolina A&T State University, and I'm going to present you our work on fault diagnosis, or I would describe it as real-time fault diagnosis that complements the work of Ali and Melchior. So just to let you know, where do we fall within the landscape of the block diagram of the project, I would place us in between the robust, as an interface in between robust perception, risk-aware planning. And I'm going to justify later on why this happens. So what is the challenge that we are trying to address? The challenge is that we would like to obtain and generate inference about the health of the aircraft under uncertainty. And at the same time, having a methodology that's somehow compatible with the existing, with the notion of assuring safety. And we would like to do that for high complex systems, high complex aircrafts. And we also want to do it in real time. So what you're going to say is a sequential Bayesian signal processing method. This is our solution, which can handle what Kevin just mentioned, non-linear and non-Gaussian systems when these representations exist in real time, and has to do it with a computationally effective way. So, and at the same time, it has to be straightforward to implement in an aircraft. So, I mean, the way that, at least from our perspective, the most important characteristics of advanced air mobility aircraft is the electric propulsion, the VTOL capability, and also the autonomy. When it comes to fault diagnosis, I mean, obviously we need early and accurate fault diagnosis, and I'm going to come to the sensitivity issue that was addressed previously. Selecting the correct sensors, and pretty much one of the visions is to limit or reduce the notion of redundancy. In other words, we do not have to have extra components. And also is what I'm going to also discuss what Irene addressed, which is the predictive maintenance capability. In other words, like figuring out if a fault is going to occur, if a fault is creeping in, essentially, if you will. So what are the benefits? The benefits is that we design techniques which are going to facilitate complex and complicated systems with many components. It's going to take place in real time, and also it's going to address the dynamic nature of the environment. Also, in addition, there is the struggle of autonomy, which is present in this aircraft, and also we need the lighter power constraints. So just to give you a little bit of the inception of this work, and when what we were discussing when we were designing the proposal. On the left-hand side is what Ali is doing, which is discrete event systems, which are much more, which have undeniably, they're having this much more effectiveness when it comes to the root cause analysis. And at the same time, they are more intuitive to a designer. Like there are obviously more benefits. I'm just saying the ones that I see are more pronounced. And at the same time, we're having these new notions of autonomy that's coming for safety for autonomy that's coming from control theory. It is how do you remain in invariant sets? I mean, how sets become invariant, and also how do we transition in between sets? So we're trying to, you know, we're having many thoughts about how these two notions, the notion of having events happening, straightforward events, and the notion of autonomy can be bridged. So what is the fault diagnostic module? The fault diagnostic module, typically, it is a component of the flight control system, and it has a symbiotic relationship with the autonomous controller. The fault diagnoser receives observations or measurements from the avionics and the sensor. At the same time, the autonomous controller provides information of what the system is trying to do. And it gives, and at the same time, the fault diagnosis modules indicates to the autonomous control modality if something is wrong, such that, for example, if a fault is detected, the aircraft is going to change its trajectory. For example, it can perform autonomous, some autonomous landing. Now, I mentioned that the fault diagnosis module is part of the flight controller, but also there is this growing vision, for example, to make it compatible with edge computing. In other words, put it in an embedded system, integrated within the component that we are monitoring. So the landscape of fault diagnosis is vast. The main category is knowledge-based methods, model-based methods, and data-driven methods. We're a little bit more traditional, and we go with the model-based methods when essentially you're having a description of the phenomenology, a mathematical description of the phenomenology that describes the underlying operation of the system that we are investigating. And essentially, when it comes to uncertainty, and we are having nonlinear systems, in the classical estimation problem, there are the options that we have are few in terms of tools. So what are the building blocks of the full diagnosis? We're having, again, as I said, models that describe the phenomenology of the system, and at the same time, we're having sensor measurements, and all of this information is going to an algorithm which resides within an embedded system, and the output is essentially, especially if we are dealing with uncertainty, is a PDF. This is what describes an uncertain state. And based on this PDF, we are tasked to decide whether or not there are faults or no at our system. So again, like the classical way to go is we're having the systems, the way that the fault space, in other words, and there's a different methods, and like the types of systems that we can have is linear Gaussian, that they never exist in the real world, and then we also have non-linear non-Gaussian, which that's the case, the general case. And there are different methods, like for example, when we are using especially when we're having Bayesian signal processing, like for example, Kalman filter, the uncentered Kalman filter, and the particle filter. Like the Kalman filter is the most limiting one. And in the standard way, what's happening is that we're having the hypothesis test, in other words, the decision test, that we test every hypothesis whether or not a fault is present to our system. We'd like to, with our design, we strive to streamline this process with certain techniques such that the procedure itself is much more computationally effective, and it's also more compatible to implementing in an embedded system. Somebody can easily program it, in other words, and transition it to the application. And it also has a direct way of performing simulations. Now, so we are following a standard estimation method for diagnosis. So what do I mean with that? We're having the classical descriptions of dynamic systems, and what we are investigating is temporal changes to the system. So I mean, for us, the temporal change to a system is synonymous to a fault. Something breaks and the dynamics change. Nevertheless, as you can see in the lower right part of hand of the picture, we can also model incipient, or what Arin mentioned is creeping faults, and this can be easily done. Now, our work has also been extended to having and to be able and identifying sensor faults. In other words, what's happening if a sensor doesn't work, and this is in one of our papers that's currently under review. So we assume that we're having a description of a component, like for example, an electromechanical, an EAM, or a motor, or we can view it as a more as a bigger subsystem, or even a system, like for example, the wing, or the entire aircraft, respectively. So this is the underlying mathematical abstraction that we assume about our system, and its description is necessary in order to derive our filter. So in the classical discrete event methods, when we are dealing, if we assume that every fault, for example, represents a state, and we are having multiple occurring faults, immediately we see that the states in this kind of dubious representations increase significantly. So the more faults that we're having, and this is the case that's going on when you are having complex aircrafts, immediately the fault space inflates. So the classical techniques that exist in the literature, I mean, the most traditional technique is the multiple models. And the multiple models for every fault state, and every fault state may incorporate multiple occurring faults. Okay, you have to perform estimation. In other words, you have to obtain an estimate of the state of the system and use this estimation to figure out, make a test whether this is the model, the correct model or not. In the case of upper end fault modes, this is a very computational intensive procedure. In other words, you must have a bank of estimators, a very large bank of estimators that you have to consistently compute in real time. And that's not practical at all. The other way to go is actually estimate if the fault occurs or not. This is a classical parameter estimation approach, nevertheless. And like in this very rough example, you can have a random walk for your parameter, but the literature has already established that the covariance increases dramatically if you're using this method. So what we have proposed and completed for the first part, we have completed for this first phase of this project, is the design of an estimation filter that incorporates hidden Markov models to be able to streamline the process of detecting faults in real time. So this step function that exists, that signifies a temporal change to the dynamics, is represented by a hidden Markov state with a transition probability that indicates if the fault mode, the probability that the fault mode in one time step is going to jump from a healthy state to a faulty state. Now, because the problem, the filter itself is becoming non-Gaussian, non-linear and non-Gaussian, there's not many choices that we can use when it comes to estimators, and particle filtering is the natural selection. So you see here, you can see here that we're having the block diagram, which follows the classical steps of it follows the classical steps of particle filtering. So what's happening? I mean, you see the execution. This is not. You see the execution of our estimation algorithm in this kind of illustrative manner. Essentially, you're having a collection of particles that jump around in between the healthy state and the binary state, and their population signifies or not if the fault occurs. There are bigger discussions about how you're gonna make the decision. Essentially, the expected value of the population of the particles, which is going to lie in between 0 and 1, is gonna help you, it's gonna give you a decision when the fault has occurred or not. The sensitivity analysis is a very big question about the false alarms. And essentially, in our design, it comes down to judiciously select the parameters to avoid. And I would say we did, when it comes to false alarms, I would say we're doing really good. Unfortunately, I don't have the results to show you. So where did we tested our algorithm? Well, the aircraft of choice was at quadcopter. We're having the classical nonlinear dynamics, the classical equations of motion, and the fault of interest is loss of power in one of the loss of power in the propellers. So this is the fault that we are investigating. And what we did is that we seeded simultaneously this loss of power in two of the propellers, such that we can investigate the identifiability capabilities of our filter. So this is what's happening, at the scenario that we investigated. We're having a reference trajectory that enters the controller. The controller also takes the state of the system, but unfortunately, the thrust, the desired thrust that the controller spits out, is not sent to the aircraft. So we're having loss of power. Now the loss of thrust, it is not observed by the diagnoser. So here you can see on the left-hand side, you can see the result of the real-time diagnostic procedure. Essentially, the output for every fault mode is the probability of failure. As I said again, it's the expected value of this hidden Markov state being in between 0 and 1. So if when this value exceeds a certain threshold, and this threshold, there are multiple techniques to find an optimal or suboptimal value for its selection, this will signify an alarm. So the faults at hand are the four loss of thrust in the four actuators, and we see a malfunction in the second and the third, second and the fourth rotor. I'm sorry. Now the time instant that the fault occurs is signified. It's shown by the step function on the left-hand side, and it takes place at the fifth time second, or the fifth time sample, or the fifth second. Now you can see that the faults are seeded simultaneously, and after the lapse of some samples, some time instances, the diagnoser was able to immediately make a decision, making a call that the fault has occurred. Now, again, some of the results, we also tested this, we also compared our algorithm with standard techniques that exist in the literature of model-based fault diagnosis, predominantly with the multiple model approach using particle filtering. And the reason we show this the result is that we did extremely well, and especially for the notion of sensitivity. So at this point, this has concluded our work on fault diagnosis, and I'm going to present you a little bit of the preliminary work that we have done on the notion of prognosis, and this is our ongoing research. Now, typically prognosis is examined by physics of failure. They are more it's more application oriented. We're trying to formulate the problem in a way that it's much more compatible with dynamical systems. And you would be surprised that there are not many things out there. Now, in general, when it comes to the prognosis, I mean, the output is calculating the remaining useful life. Essentially, this is a probability that a fault it's going to occur. I know that Frank is gonna yell at me, so I'm just gonna move forward. So, okay, where are we going with that? Really quickly, just two brief comments. Well, we're trying right now we're trying to make prognosis much more compatible with these new notions that exist about reachability and about safety of autonomous systems. So we would like to somehow start using the language that it's using in this research problem. Why finding the remaining useful life? It is important. It is important because you know when a catastrophic failure is gonna happen, and your controller may adjust the trajectory of the aircraft. Where we're going to apply these things? I mean, after we're having ongoing discussions with Reno and Urbana Champaign, and the platform of choice, which is more compatible for us, I believe, it's Minihawk. Okay, here is my graduate student, an army of one, who is doing all of this fantastic work. So I'm happy to take your questions.
So we can take one question.
Yeah. Can I?
Go ahead.
Hi, Yanis. Thank you for your presentation. It was very interesting.
Thank you.
And it's interesting that you're using a model-based approach, which is, could give you some prognostications. I was wondering on the diagnostics, are you using a deviation from some place? You mentioned, is it like magnitude based or how exactly is your FD algorithm working?
Okay. It is well. So we're trying to when we're dealing with dynamical systems, in other words, systems that changes with time. The standard threshold detection does not apply anymore because you're having something that has transients and it moves around.
Right.
So we manage with this, the beauty of this hidden Markov model approach that we are using in order to design essentially what it is called a detection filter. It is a filter is something that is doing estimation, and in that case, it's detection because it tells you whether or not something wrong has happened. Essentially, it is coming. This decision is coming from a PDF, and this is the PDF of this hidden Markov state. Now, we can theoretically show that the expected value of this hidden Markov state, it is essentially what we would call a decision test, the classical likelihood ratio test that you decide whether or not something, a hypothesis is taking place. Well, it signifies completely that thing, and you are performing even something stronger. It is a posterior test, which is even more stronger than the likelihood ratio test. So just taking the expected value of this, essentially hybrid state is a very efficient way to have some sort of a decision variable. So I'm not sure if I answered your question.
Thank you. Well, I might suggest something which might turn out to be more computationally efficient. And that would be, since you have the states that you're using, you might want, and you have the nominal characterization of your model, otherwise it wouldn't be a model-based. You might want to use a direction-based test, which means, because magnitudes can be affected by momentary disturbances. It might throw you off, but direction doesn't change momentarily just due to noise. It would change due to a fault. So if you find that, it's essentially correlating in a way, finding the deviation, the angle, and that's much faster. I will try to dig up. I have a couple of algorithms that now I don't have my all my records here in the US. I have them in Greece, but
Okay.
I will try to send you because I think you might find in my experience, this gives you order of magnitude in time improvement in both real-time diagnosis and also the accuracy. So you might want to consider it. It's a more accurate way of dealing with, directionality doesn't really change due to noise. It changes due to a fault. And that could
Well,
be a discriminating.
We're gonna definitely reach out.
Yeah,
we'll
let's
be happy to
because
investigate.
we did that for the LISA Pathfinder for small thrusters, very minuscule, and Astrium had their algorithm, and ours worked much better. So you might want to try. I'll try. Thank you very much.
Thank you, Lena.
Yeah.
So we'll move on, and thank you for this live discussion. Do we have Melchior here?
Yeah. I'm here.
Okay.
Let me share my screen. Just a sec. Let's see where we are. Just a second. There we go. Okay. Can you see me, hear me?
Yep, no problem.
Okay. I'll try to go fast to make up for a little bit of the time that we spent on these very useful questions, actually.
Actually, we can give you extra 5 minutes because we have a short break after this.
Okay.
So you can present with your original pace. No worries.
Okay. All right. Thank you, Sheng. Okay. So yes, I'm always glad to be the third person in our TC to presenting because Yanis and Ali give such a wonderful overview of kind of where we fit in and kind of what the background for a lot of our work is. So I'm the third member of the team, and the idea is that we perform reachability analysis based partly on the kind of fault diagnosis and prediction results that Ali and Yanis built. So let me just kind of give an overview for what is the long or I guess the large scale picture of perhaps even our TC altogether. So once again, reachability analysis. My name is Melchior Ornick from Illinois. So the idea of fault diagnosis, of control in under kind of adversity altogether, is to develop maximal understanding in the face of minimal knowledge. And in some sense, this is a classical problem, right? Reach your control objective under some lack of knowledge about the dynamics, about the environment, about whatever it is. The issue, which of course has been recognized in civil aviation and at the regulation level and at kind of in every other autonomy domain, is the fact that an objective might not be reachable. And so I usually when I have this slide, there's a video of an aircraft that lost an engine, and it's a small Cessna aircraft. He's 9 miles out of the airport, and he says, well, I can't make it to the airport. And then he finds a reachable kind of target. He finds a place where he thinks he can land, or where he is certain he can land. And then he plans how to get there. And in the end, the pilot survives and everything is okay. And so this is broadly the behavior that we wish to emulate. So my slide is not moving, just a sec. There we go. So what we're seeking to develop are certifiable capabilities. And as I will show, they're kind of on the short horizon, on the short time span. But basically, given an adverse event, we switch from a nominal transition model, call it nominal dynamics or whatever it is, to a partially known novel transition model, so to some sort of a partial model. This model is This partial knowledge comes from some invariance of the nominal transition model, maybe through design knowledge, through the knowledge of, hey, this thing still works, or this is still how it should work, even though something bad happened to another part of the airframe. It comes from partly from physical laws. Importantly, for this discussion, it comes from fault detection and identification, right? So Yanis and Ali come and tell me, hey, this is what is wrong with the airplane. We don't have a perfect model of it, but we can provide you some bounds. We can provide you some structure of what is wrong. And now here, do some magic with this partially known model. Of course, we might have some also knowledge from sensing in terms of, hey, we try something, we see how it works. So we have some sort of a partially imperfectly observed current path trajectory. We want to mix up this whole soup into providing a conservative estimate of completable tasks. And what I mean here by conservative estimate of completable tasks is we don't want to have false positives, right? We know that we might have false negatives. Our system might be more capable than we know, and that's natural because we only have a partially known model. But we at least want to certify, hey, the system is able to produce this maneuver. The system is able to reach this state. Ideally, we want to do this kind of iteratively. Before, during, provably learning online how to complete a task, how to perform kind of higher level planning, how to gain more information, and so on. So within the big scope of our ULI project, we come into the kind of reachable target and reachability analysis story. So we want to, as a fault is occurring or after an adverse event, we want to figure out, hey, this is what the system is still capable of doing, at least over a short time horizon. And we want to pass this on to control planning, to kind of trajectory optimization, to target allocation, whatever it is. So we're kind of sitting in the middle, essentially. Now, when I say we have a partially known model, the mathematical framework of the model that I'm interested in, and it's very similar to what Yanis is interested in naturally, is continuous time. So x dot equals f of xu, where u lies in some sort of a set u of possible inputs. X is the system state. The problem is that f is unknown. So we have a nominal f, but after an adverse event, this f changes into what I'll call f question mark. This is an unknown function. And what I mean by unknown function is not necessarily a small disturbance, not necessarily unknown parameters, although that is certainly one of the options, but it is potentially a substantially unknown function. I have a video here. So in this case, and I think this is similar to a video I also showed last year, right? The dynamics of this falling aircraft right now, which was RC controlled, are not a small change in a few parameters. They're not a small disturbance, right? This is a completely new function. So what do we do in such a case? After a change in dynamics, and this is certainly what Yanis was mentioning, I think, at the end of his talk. After a change in dynamics, the system can almost certainly not use the same control law to reach its target. The system might not be able to reach its original target using any control law. And so the big question that our part of TC3 is trying to answer is, what is the system certifiably capable of doing? And this is where Yanis's and Ali's work comes crucially into our work, because if we don't know anything about the system, then nothing is certain, right? Everything can change half a second from now, and I cannot guarantee anything. However, if I do have some set of possible dynamics that are consistent with the current knowledge, and so this is probably not going to be one particular model, but some set of models, I can find the reachable sets for this set of models. I'll call that RF, RF tilde, and I can intersect all of them. If a state is in the intersection of this of all of these reachable sets, certainly it is in the reachable set for whichever of these models is the actual ground truth. And so this, what I call the guaranteed reachable set, RG of X0, produces a under approximation of the true reachable set of the system. Now, in theory, I defined all of this, and the problem is that I'm asking here to intersect possibly infinitely many reachable sets of nonlinear control systems, right? In practice, it's not very doable. So the question is, how do I do something meaningful about it? Our method so far has been, instead of computing the reachable sets and then integrating all of them, let us find the guaranteed velocities. So let's find the velocities that the system can pursue at a given time. And let's find all trajectories obtained by integrating those. This will give an under approximation, and that's a pretty easy proof, that this will provide an under approximation of the guaranteed reachable set. Now, this became easier, one level easier, instead of intersecting all the reachable sets. Now I'm intersecting the possible velocities. It's still not easy. So the question is, how do I guarantee the velocities at time t? And so far, and this is certainly something that we're kind of building up on as we're developing better models for fault diagnosis, velocities guaranteed at time t are the velocities that are guaranteed at time 0. So what can I do right now? Modulo how much can things go wrong in the future. So modulo some sort of a maximal system wildness. We can use online system ID, we can use fault diagnosis, or fault identification, I guess, for figuring out some of the velocities that the system can pursue right now. And then we can project that in the future. And I think that this kind of goes to half of Irene's question from Ali's talk. We can kind of project that in the future using this idea of maximal system wildness to see what's going on, what we can possibly count on still being accessible in the future. This bound on the change of available velocities could come from known system parameters or Lipschitz bound on the change in the system dynamics. For control affine systems, which are a very vast class of nonlinear systems, we can determine this set of available velocities, but it is still ugly. It is possible to under approximate it, and so this is what we were working on. This is partly a picture from year one of kind of how to make all of this computationally feasible. And instead of this weird blue set, which does not have a particular geometric representation, we can under approximate it by a ball, by a polygon, by an ellipsoid. The idea then is that the guaranteed reachable set is a reachable set of a simpler control system. And we've played with some initial models on there. The issue is that, first of all of these results are very short time, which is natural, right? If I don't have significant knowledge about the system, all I can do is provide some very short time guarantees. So we're wondering how to make this better. And we're wondering, how can I better use the information that I will get about the system, whether through physical laws, whether through some design knowledge, whether through Yanis and Ali. And so what we've been working on lately is this notion, or a part of what we've been working on lately, is this notion of guaranteed reachability on a manifold, right? So what I mean by on a manifold is I know that X lies in some set M. This set M, this manifold M, could come from some physical knowledge, could come from an a priori safety constraint, could come from some knowledge of a conserved quantity. So something that I know does not change after a particular fault. And so in particular, fault detection or fault identification could tell me something about this conserved quantity. Now, the problem here is that if X lies in a manifold M, that means that X dot does not lie in Euclidean space anymore. It lies in the tangent space of the manifold. And so what do I do then? The guaranteed velocities at different times no longer even live in the same space. They live in different tangent spaces. Whatever I had about the maximum system degradation, which was kind of based on Lipschitz constants, is now non-trivial to define, because now the Lipschitz constant depends on the paths or the geodesics along this manifold. And you could attack me on that. And you could say, okay, you're selling a theory that doesn't make sense. Why don't you just embed everything into a Euclidean space? The first answer, which I kind of feel obliged to provide simply from kind of being a mathematician, is it doesn't feel right, right? We're not using all the structure that we have. But there are practical reasons not to do that. The first one is whatever information you had about the manifold, whatever kind of long-term information you had about the system structure gets lost. Your Lipschitz constants get worse, and you also lose full actuation, which is important if you know that the system is fully actuated on a manifold. And then you embed this manifold into a higher dimensional space. Now you have a degenerate system in this higher dimensional space. And that's going to make it harder to create control laws for this system. This is just speaking of the theory of things. There is another significant challenge here, which is that the system, how do we do anything computationally? How do we do anything numerically? How do we even solve an ODE natively on a manifold? And so the idea of what we're doing is still the same. But the under approximations of guaranteed velocities now depend on some pretty heavy math. They depend on the Riemannian metric tensor and covariant derivatives, or the choice of connection. Importantly, for flat manifolds, for cases where we don't have this additional information, we recover previous results for Euclidean spaces. And so our numerical example is kind of a classical example that, or a classical manifold that people use because it is meaningful for autonomy and for robotics. So how to operate on the space of rotations on SO3. So this is difficult to meaningfully even think about in Euclidean space. It is useful for applications. And so we can compute this, this guaranteed reachable set, or under approximate the guaranteed reachable set right now. But now that I have kind of established what the system is capable of doing, we still don't know how to do it. And I'm not even speaking about kind of long-term control synthesis and planning that the other TCs are working on and that we want to kind of transfer our information to. I'm saying in this short time, as I'm learning, as I'm performing this short maneuver where my lack of knowledge is still such that I can't turn on L1, or I can't turn on kind of methods of motion planning or mission planning, I want to still be able to control the system somehow. And so I want to have this kind of end-to-end planning, learning, and control. I want to figure out what tasks can be provably completed, and that's what I was talking about so far. But I also want to know what I need to learn in order to be able to complete it, or in order to be able to get better models. And I need to have some sort of assured control. I need to know that as I'm learning this, the system isn't completely going to fall apart. And so I want to have these kind of short-term controllers that still leave the system safe in some sense. In short, I want to allow the vehicle time to get smarter. I'm not claiming that this should be used for control. We should have better models, but I want to give some time before I die. And so what I want to do is perform some sort of local system ID. The way that we are doing this, and this is something that we're very interested in working on right now, the way that we're doing this is if a system is at state X, applying a constant control U, this is a wrong year for the paper, but okay. Applying a constant control U plus and observing the system response provides an approximation for the local dynamics of the system. For control affine systems, in theory, we can entirely learn the local dynamics by quickly sequentially applying affinely independent controls. This is nice to write. Of course, with actual aircraft, there are limitations to what I can mean by saying quickly sequentially applying. So there is resolution to the kind of sensor, to the sensor speed. There's resolution to the speed of changing actuator inputs and to the sizes of actuators. So, but certainly we can provide some bounds on learning these local dynamics. If we know them, we can choose an input that appears to work well right now. And so we were playing with something called the goodness function. The problem is that this has no guarantees. How do I even choose the goodness function? And so we have a kind of a three-step method of choose a target or a state guarantee to be reachable. Our reachability computations produce a guaranteed trajectory, and we want to provably approximately follow this guaranteed trajectory. To do that, we will perform some short-time online learning and try to track this trajectory. We can do this. We have some theory that establishes bounds on the system performance. And of course, these bounds depend on the wildness of the system dynamics, but they also depend on the resolution of actuator and sensor. So let me just end with saying, okay, we recognize that what we're doing here is imperfect, because right now we are forgetting about all the memory. And this comes, I think, to the second part of Irene's question of, okay, is there some sort of prediction that we can do here? Is there something where we can draw from history? And indeed, trying to learn from scratch is wasteful. And so what we're playing with right now is finding the most likely dynamics given the observations and learning and continuing to learn. So these most likely dynamics need to take into account that samples might have come from slightly different states, from slightly different dynamics before, and that these dynamics might change as the fault develops. But we shouldn't just throw everything away immediately. And so what we were playing with that is a more kind of, or what we introduced there is a more, I would say, advanced learning-based kind of, I guess, learning-based estimator and controller for the system based on what we call change-conscious maximum likelihood estimation, and we tested that on the Guam model. The bigger picture, of course, is that, hey, we won't just have changes in dynamics. We might have partial loss of control. We might have actuator degradation, sensing faults, time delays, and so on. The point is that adverse events cause intricately structured changes, and that classical methods assume significant structure that might not be available, or simplistic structure that might not be available, and attempt to reach a possibly unattainable task. And so what we're trying to do is determine what the system can do, even when we don't know everything about it. The first step to that, we claim, is reachability analysis. And we're pursuing geometry-based methods for unknown systems. I claim that this is mathematically challenging, that this is applicable, and connecting our work to TC3 and to this further effort, it is heavily dependent on identifying the remaining invariant system knowledge. Let me stop here. Thank you.
Thank you, Milker. There's one question from Kevin in the chat.
Yes,
you can open it and answer that question.
Let me read it.
It's not so much a question, just a comment. You know, we've done lots of studies on indirect adaptive versus direct adaptive. And on unstable aircraft, you don't have time to identify anything. The game is over in 200 milliseconds if the airplane's departing.
Yeah.
So okay, that's just really a comment.
Yeah, no, I certainly agree with you, and whatever we can do is predicated under heavy assumptions on the system dynamics still being very, I wouldn't call them stable, but very tame in a sense. What I think is meaningful within the context of this ULI is that we should not be trying to identify things from scratch. We should try to use as much as possible of the invariant features that can be provided by Ali and Yanis's work, and try to account for those when calculating the guaranteed reachable set. So I agree with you, and I claim that in fact learning everything from scratch is not a feasible option, probably. Okay, I see I'm slightly over time, but hopefully you told me I get extra 5 minutes, so I'm good.
Yep, you're fine. You still have 1 minute left in the Q&A. So if nobody has any more questions, then we can enter our 10-minute break time. So we'll resume in, let me see, we'll resume in 10:30. And in the meantime, for those of you who presented in the morning, we noticed that you have updated slides compared with what we have received yesterday. So please kindly update your latest slides so that we can later share with the advisory board. And other than that, we're going to the break, and we're going to leave this room open so that if you have questions, you can use the time to chat. See you soon. All right. Welcome back, everybody. And we're about to continue our review, and we'll have Vasu next to present TC4 research update. So Vasu, I see you have camera on, so you can share your screen.
Can you see my screen?
Yep.
Okay, great. Shall I start?
Sure, go ahead.
Okay, so hello everybody. I'm Vasu Sarapaka from University of Illinois, and I'll be talking about network logistics and planning problems in airspace management. So I'm a part of TC4, testing, evaluation, integration towards technology transfer. So basically our group comprises Petros, Youngjan, Christos, and Andy Smith, and are basically involved with facilitating other groups for testing and evaluation. However, my talk and my work is a little bit different in the sense that I'm talking about, as I said, network logistics and planning problems in airspace management. Basically, my goal here is to develop a framework for multi-objective resource management. So briefly, basically coordinating multiple elements within airspace, so that essentially developing an algorithmic framework to enable traffic management systems to essentially manage the unmanned air systems and the resources, the ground and air infrastructure. And so basically our work has been coming up with abstracting the details on planning and logistic problems in the underlying airspace management problem. So this is where we stand in the context of the proposal of the whole project. Now let me tell you where we are. Today's talk would be in the context of this airspace management work. So last annual review meeting, I had essentially abstracted out a lot of problems where we said logistics and planning problems like resource allocation, traveling, vehicle routing, scheduling, flight plan prioritization, etc., and which are all difficult problems by themselves, and there are algorithms that solve each of them. However, in the context of this airspace management, there are many problems that come together. So we need a platform that can address each of these problems and combinations of these problems, along with various different kinds of constraints to address them. And last time I had presented a algorithmic framework, which we call parameterized sequential decision-making framework. So over the last year, we have been consolidating that framework. We have been adding lots of new capabilities to it. And then, like, for example, adding different kinds of capacity constraints, topological constraints, making sensitivity analysis with respect to the parameters, and then robustness, uncertainty, etc. And then last time there was a comment which we have taken seriously, in which was like to talk more about scalability and design more, which was in our plan, but now I'll be spending quite a bit time on scalability and then including dynamic constraints to the set of things that we have. So just to give you an idea of the kind of approaches that we have been using for coming up with solutions which actually help with all these different kinds of problems, logistics problems like routing, scheduling, resource allocation, everything together. We have used concepts from statistical physics and statistics, controls and optimization, and machine learning. So it's a brief outline of what we'll be seeing now. Basically, I give a brief recap of the framework of the SDM framework, the parameterized sequential decision making. I'll talk about the central concepts, and then I'll give you some examples that we have solved just to give you a flavor of the kind of problems that we are working with. Then I'll spend a little bit time on for scalable algorithms, and where I'll give you a visualization of decision parameter space, and then what are the difficult points in terms of computational expense, and then how we are addressing them. I'll talk about some ongoing work there, and then plans for the next year. So this is a baseline para-SDM problem. So I told you that there are lots of different kinds of problems that are coming up, and becomes very difficult to accommodate all of them in the same framework. However, what we showed last time was that if we can view a new class of optimization problems that actually subsume all those problems, and you can see most of those problems as a deviation or a variation of this problem that I'm going to describe is called simultaneous facility location and path optimization. And if I can solve this, and then if I can add some kinds of flexibility in terms of the kinds of constraints that I can use, then you can actually you have a platform which can address all those problems. So here's the problem. You can think of these blue circles here as a sensor network, which have got a lot of data that need to be transmitted to say a common destination. And this transmission of data can happen through say a network of routers. And then the question would be to find the optimal router path or optimal route of these data packets to the destination. Now, such a problem would be a routing problem, and that can be easily thought of as a as a dynamic program, or in a stochastic case, it can be thought of as a MDP, where you have essentially these states, and each state can take an action to go to the next router, and you have to find the shortest path in such a place. Now, however, this problem becomes much more difficult, actually becomes NP hard, if I also say that you have the freedom of allocating where these resources can be, where these routers can be. You also need to decide the locations of these routers so that the total communication cost is minimized. In such a case, I'm minimizing not only with respect to paths. Here, gamma is a path. So not only with respect to paths, here eta of gamma comma I is essentially saying that if I start from the initial sensor, there is one particular path. So eta is a binary variable which takes 1 on the one path and 0 on all other paths. So we have to find out the best such path and best locations, best facility locations, so that the total communication cost is reduced. Not only the path. So the shortest path problem would be a dynamic program or MDP problem. Shortest path problem, where all simultaneous with these parameters, becomes a very difficult problem, which is what we are calling as a FLPO problem or a para-SDM problem, baseline para-SDM problem. And last time, no, actually we did some consolidation of our codes, and we have gotten and I presented these things. So I'll not spend too much time. Maybe I'll describe you one of these problems to give you the flavor of the kind of problems we are doing. So here you have this many vehicles. So for example, vehicle V1, V2, V3, V4. They are coming with different kinds, with different charges. So say 0.5, 0.3, and 0.4 are the charges that they come into this network with, and they have the destinations, say D1, D2, D3, etc. And they have to reach, and then we have to find out the routing and placement of these of the charging stations, so that the total all the routes are satisfied, and you do it with the minimum. And so that they go to the appropriate charging levels whenever the destination is far away, that you cannot do with the initial charge. So these problems, there are very few algorithms that can satisfy that actually resolve both routing and facility problems. We had to go for some to compare. We had to go for some algorithms like genetic algorithm, etc. And we could see that that the proposed method was much faster than these other algorithms. And I'm skipping on these other things also. So here we showed routing and facility locations. Here we could show at least scheduling and routing and congestion avoidance. And then we also did shop this is called job shop scheduling, or basically you have predefined flight plans for many drones, and then you want to schedule them so that all the facility nodes are adequately reached. So these are the problems that we did, and I presented last time. And now we have actually added lots of lots of constraints, etc., that we can add to this framework. For example, we have link capacity constraints, node capacity constraints. So basically, we can say that traffic. Sorry, I think I got a wrong picture here for the here. But so essentially, we can have constraints on how much traffic can pass through each link. Say link between F1 and F2, for example. We can have things like also like capacities on how much each how much traffic can pass through each facility. We can have some topological constraints. For example, here we have put a constraint that each facility can get data from maximum one another facility, and so on. So you can have a topological constraints, network constraints on these problems. All these are acceptable under the para-SDM framework that we're developing. And then as a side thing, we also get for almost for free, we get some sensitivity analysis where we can find the how sensitive the solution is with respect to different parameters. For example, here we have found the sensitivity with respect to the locations of the sensors, and you can see here that like the blue ones are the cyan ones are high sensitive, and the blue ones are low sensitive, and so on. So you can characterize like that, and then you can also even add robustness. Given the kind of uncertainty models you may have, you can include that into the framework, and you can actually get some robust solutions. Now, so one of our stresses has been to have to work with large number of nodes and facilities. And our current algorithms, we did actually have done improvements in which now we can run these algorithms for pretty large, 10,000 nodes and 50 facilities, lots of combinations, and it takes around 2.5 hours. So still not the best. So what I'll talk about now would be more methods to make these to improve the scalability of this algorithm. So to give you an idea of what is the parameter space that we are working with. So this was, if you remember, this was the original problem we had, where we had to minimize, basically optimize over the facility locations, right? In the baseline problem, and then this paths. Basically, we had this binary variable which associated to path 1. Value 1 to the optimal path would get the value 1, and everything else would get 0. So what we do first is we relax this problem to facility locations and probability distributions, not binary variable 0, 1, but probability distribution 0, 1 on the space of paths. And then we add an entropy term which measures the randomness of this distribution that we have added. Nice. So basically, the corresponding function, the cost function that we get, depends on the facility locations, on these distributions from action and state variables, and then this annealing parameter beta, and it should be the nice part about our algorithm is that as beta goes to infinity, so we call that as annealing parameter. Actually, this cost function becomes the original cost function. Okay, that is pretty obvious, because if beta goes to infinity, this thing goes to 0. But another interesting aspect is that these distributions actually become hard, and they become binary distributions. So we get that for free. So we have relaxed the problem, but then we get the solution to the original problem for free as beta goes to infinity. So these are the three axes that we want to minimize about. And now for every y, we have to solve. So basically for every fixed location, I said that the corresponding problem would be a dynamic program. So we have to solve a dynamic program. Now, in many of the problems that we are considering, we can show actually that we can explicitly get PK of A given S. So that this whole dynamic program part is avoided in many of the problems. The baseline FLPO problem, for example, we have, if I know Y, I know how to get the PK of A given S in an explicit form. So we have that solution. Now, if we don't, in some other problems, we don't have that solution, in which case we have to solve the dynamic program. So for every Y, we have to find a dynamic program. Then we have to optimize over Y, and then we have to do the annealing. So this is the computational complexity of this problem. So there are three. So basically, these are the three loops that we have to run. So basically, we want to minimize annealing, where we are changing beta. In each beta, we have to find the minimization of this cost function for a given location, facility location vector. Then that facility location vector. Now, in some problems, we know how the solution of the dynamic program or those probabilities. Or if we don't know, then we have to run the dynamic program and get that. So these are the complicated. This is a costly. If you have to compute the dynamic program, that's a costly part. And then the gradient descent to find minimum of f of y, that is another part. So what I'll do is first I'll talk about something that we are using now to get gradient descent. And then I'll talk about like how we are taking care of this. So the two ideas we are doing is we are using some ideas from like the control barrier functions from control for the gradient descent, decreasing the computations for that. And then we're using some machine learning ideas to decrease the other computations. So typically for gradient descent, for our problems, they are very non-convex cost functions. And over that, with these constraints, a lot of these constraints, it becomes very difficult to come with solvers that do a good job or a fast job in solving the gradient. Basically, this is a very costly problem to do the gradient descent on such problems. So what we are doing now is we are taking these static problems and converting them into dynamic problems, dynamic control problems. And so replacing the y, which was the decision variable, by u, where y dot is equal to u. And then what we do is we use the control barrier function idea, where at every step you can pose a optimization on u, where these are actually linear in u. These constraints are linear in u. And they will make sure that you're always in the feasible region, and while also satisfying that you're going to the local minima. And then and you can solve this. These are very fast to solve, and we get a lot of advantage from that. So let me go a little bit quickly. So here is an example which shows that where we have taken lots of where we have a lot of sensors here, and then there is but at any time t, there is a demand for a certain resource, and only few of those sensors can be activated, which is fixed. For example, only 2 sensors can be activated over all 100 sensors, and such a way that they can provide for the demand. And we have to find out what weight of them they can provide to be nearest to the demand. So which two? So the problem is which 2 sensors to be, or which 2 resources to be chosen, resource vectors to be chosen, and then at what percentage, at what weight should we choose them so that they satisfy a certain demand. Now this is and now since we are using now suppose we can even include dynamic constraints now, in which, for example, if this demand is dynamic, then how do we change these numbers? We want to solve the problem for every time t of choosing them, and also coming up with how to choose those values. And what we did was we used this problem, and when we actually ran this problem, so here is what we get from a solver, and the other is from our method. We get this exact same solutions. So the solutions we mimic, however, we are like 5 times faster. What are these slides? What are these graphs showing? This is actually showing the which of the 100 which two of the 100 sensors are being chosen, and then also, and this is showing the error. So let me go. I think I'm going a little bit. Let me increase the pace. And for the other part, where we have got this computing of f of y, which requires computing the dynamic program and also finding out the derivatives of the, like, some kind of gradients of them, we are actually using neural nets to approximate them. And so these are the idea. These are ongoing work. We have currently done approximating this part, but later we want to do, in which we want to give inputs for everything, for even for the facility location, and then S and state and action, and then see what is the corresponding lambda. I have not spent much time on talking about lambda. Knowing these lambdas at every stage helps me creating this F. Okay, F depends on what these lambda values are, and we are learning. Basically, the short take would be that we are exploiting the structure of these of our algorithm to create appropriate neural net, appropriate features to learn, so that your learning, the training would be take relatively lesser data, and then we can get that. We can develop. We can get function approximations for these solutions. I will very quickly go over this. So basically, we did apply for the dynamic program part, and we got for different beta values, we are getting pretty good prediction minus target is predicting the solutions to the target. We get very good matches there. And then I'll end up with one final idea, where what we are also doing is we have this algorithmic solver. So what we are trying to do is we are generating a lot of big data set with the input scenarios and what are the corresponding outputs, say facility locations and the routes. And then we are learning the entire thing and trying to predict the optimal routes for new scenarios. Now here we are doing both in the black box and open white box approaches, where in the black box we just try to fit the data, input and output data, while in the gray box or white box we are using some of the features of the solutions and incorporating into that. So here is a result where we show that the prediction for the routing problem was pretty good. And lacking in time, so let me just finish with this. So plans for the next year will be consolidating our all of the different features together into one together, and then we will run it on the airspace problem that I had presented in the last meet, essentially, which consists of hierarchy of airspace volumes, and then we have different kinds of problems of facility location, routing, scheduling, etc. on that whole volume of problems, and then we would pose that and do very extensive simulations with that. And then we are doing some work with Christos's group, where we would be applying on a small scale multi drone. It cannot be very large numbers because of the experimental constraints, and then with placing of charging stations to increase the travel life. So here are some papers, and thank you. Any questions?
We have time for one question. Irene, any questions?
No, sorry, still trying to digest a lot of information. So looking forward to following up with that. Thank you.
Okay, thank you. Sure, I'll be available on chat.
All right, in case we don't have any more questions, we can have the next speaker ready. So Petros, are you here, Petros? Okay, I can see Petros. Okay, screen being shared.
I'm just fixing some things up.
Okay. Take your time.
So you see my screen here?
Yes.
Okay.
Okay, you can start.
All right, great. So what I'll be presenting are things that we have been doing along TC4, and that's primarily work that Hyunjin has performed on creating simulators and realistic environments to test our algorithms and platforms. So I'm gonna go quickly over an overview of what we're doing, and then Hyunjin will discuss specific developments, including the integration of Guam model into the 3D simulation and the incorporation of autopilot software in the loop with this simulation. We will also talk briefly and explain how the previous simulation developments will interface with the hardware. The initial step is to utilize the autopilot computer and the mobile GPU within the 3D simulation environment. Finally, we'll talk about the GitHub repository for the simulation, which serves as an integration hub for work from the other groups. Okay, so that's the overview, and let me say a few things about how we stand according to the plan we had. So, as I said, we added two, well, I didn't say, but yeah, we added two 3D vehicle models into the Unreal Carla environment, the WISC Cora and UNR's Minihawk. The WISC Cora is integrated with NASA's Guam model, while the UNR Minihawk is integrated with the software in the loop simulation developed by Christos's group at UNR. So this software in the loop simulation supports M4, milestones M4 and M5, which involve running autopilot software on UAV computers for diagnostic and analytical purposes. So testing the software intended for autopilot computer, this way the simulation sets the stage for a smooth transition to real flight demonstrations. So to further work on the demonstrations, we have developed a hardware in the loop, or we are actually in the process of developing a hardware in the loop simulation for next year real flight demonstration. The 3D simulation will remain valuable for real flight tests by enabling the simulation of an urban environment, complete with camera images and LiDAR signals from surrounding vehicles and buildings. This simulated sensor can be transmitted to the mobile GPU computer on the vehicle during flight tests in Reno, and the essence of this Unreal Carla 3D simulation can be augmented with real flight data, creating this way a more integrated demonstration. Okay. So that's, I guess, what I said. Okay, so next, I'm gonna give you some idea of what this simulation looks like now, and Hyunjin will talk much more about the details. So a recurring thing in discussions with other TCs regarding the demo scenario is landing in a GPS denied environment, And as we know, many of the TCs are related to this kind of case. All right, so here is the video and that has been developed that uses Guam vehicle, so Guam dynamics, and the 3D model of the vehicle is the Wiscora, that is a passenger carrying VTOL vehicle, as you can see. The Unreal Carla is developed for developing autonomous car. However, we modified the environment by adding the 3D model of the VTOL vehicle and replacing car dynamics with the Guam model. So the vision paint landing that you're showing, that is showing here, we use YOLO network to detect the helipad landing site. And as you see, the object detection results displayed with the bounding boxes, and we use a Bayesian recursive update. The overlaps of the bounding boxes from the previous time steps serve as a likelihood function for the update step in the Bayesian recursive update method. So in this landing situation, we employ a simple proportional controller that adjusts the velocity command to maintain alignment between the center of the camera and the bounding box. And so also here we have developed a software in the loop simulation for the Mini Hawk that you see here, some pictures and video. And also we have developed a simulation capability to change environmental factors such as weather and lighting, and that will provide the diverse data for training and testing. Okay, so I believe that the simulation environment will be valuable for next year's demo, and particularly for testing the vision-based landing scenario, which is a major theme of the demonstration. Furthermore, by augmenting this simulation with real flight data, we can test and demonstrate the vision-based navigation algorithms across various scenarios. So Hyun Jin will continue this presentation and provide, as I said, the details on all of that. And well, thank you, and Hyun Jin will take over.
Thank you, Christos. Thank you, Petros. Okay. So maybe this is going to be more convenient if I share screen here, because I need to click the slide. So let me share those. Okay, because Petros already showed you the overview videos. The other parts are some details, but Petros showed you the main essence of this presentation slide already. What did we do in this first phase? So many guys here already know that we are using Kala, that is Unreal game environment developed for autonomous car simulation. We are utilizing this because this is very convenient for us to have different sensor configuration compared to other tools. So, and also it supports multi-vehicle scenarios. So I've been thinking that this is useful. An update from the previous is Dr. Fan in MIT, I think they successfully completely migrate NASA's generic UAM model from MATLAB into JAX framework. So I started to use this because our default development languages in our simulation environment is actually Python. So JAX has been more convenient for us to use, so we use this. To give you a brief intro about JAX is something similar to PyTorch that supports parallel computing from GPUs, and also it has automatic differentiation that can be useful for calculating Jacobian or Hessian possibly for linearization. So I use their batch sample generation script part to get just this state transition, because the simulation environment, game environment, we need just one state transition. So we are using this. And this work was the use of JAX-GUAM with the color environment was done actually not by me. It was done by a student in Naira's group, and also a student in Dr. Pan's group, and also Ayush in Professor Louis' group. They worked on this. I'm actually kind of using this. All right, this is what I did. I downloaded this WISC Cora. It used to be Kitty Hawk, now it's a WISC 3D model from computer generated creator, and then import it into Blender, and then I import it again into Unreal Game Engines, and then I wrote some graphical script so that the animation of propeller is working. So it actually the propellers in the simulation is actually rotating using Unreal Game Engine. It is interesting that there are existing other good-looking VTOL graphics that is available from those websites. I plan to use those in future so that the multi-car movement in Ayush's presentation yesterday can be replaced with those vehicles. I want to introduce you some use case of this color Unreal, maybe ULI environment. One use case is I'm following the vision-based landing work by Dr. Papachristos at UNR. So you can see that here there is the bounding box of the this 4-leg robot from Boston Dynamics. And then they also have this April tag, so that way it works is, I think, I need to get it confirmed by Papachristos, but they use something like a YOLO to detect this landing spot at a far distance as it gets close to the real landing spot, and then they start to use April tag for more precise controlled landing. What I did in this environment is I did until just using YOLO network object detector for getting closer to the landing spot. So we trained YOLO V8 from Ultralytics using the 5,000 helipad images downloaded from Google Maps. I did not curate this data, but there is some script available that actually automatically generated training data images with the label. So we had the training validation data set that is about 5,000 samples. Using some small size YOLO, it is only 20 megabytes, so it is known to be runnable on small mobile GPU device. And then I directly used it in the simulation. Looks like it works with all helipad object in the simulation. And also I tested with the drone launchpad images that I collected recently. Without any further training, looks like, because the 5,000 sample is maybe large enough to generalize in the simulation environment, also with the real images. As a proof of concept, basically to demonstrate the usefulness of this simulator, I implemented very simple proportional controller. As you can see, I get horizontal error 1, error 2 to keep the camera view at the center. How can I? Yeah, that's fine. You have seen this already. So, and then the size of this bounding box can have some information about the distance to the landing spot. So I use very simple proportional controller. Although this is simple, and also I would say that this is very controlled simulation because I make sure to start at the initial position where you actually see these landing spots from the camera view. But however, once you get to the point, maybe using GPS, then you can use this vision-based landing without using GPS. So it is somewhat relevant to GPS-denied environment simulation. So to enhance the performance, the future work is, of course, integrate all that the advanced work from other TCs, and also some standard tool, including visual inertial odometry, and also vertical height sensors, and camera model. I did not even use camera model in this one. Camera model gives you basically pointing vector to object corresponding to the pixel. So that probably improved it more. I think that another motivation of this very simple environment is to address some research interest that I have. I'm very interested about updating machine learning model and also nominal vehicle dynamics if it is needed. How do we know the update is needed? Very practical motivation probably is I think that if we see the performance degradation, then maybe this can be an indicator of the using wrong model, or borrowing all that work in uncertainty estimation for machine learning model. I can also still kind of quantify the uncertainty. For example, the variance of the ensemble model, like 5 different models can be increased when the model are seeing the new patterns in the data, right? So this is well known. So we are using this. So this is like complete overview that I envisioned. I wanted to update both vehicle dynamics and also not only vehicle dynamics, also sort of the environment plus vehicle dynamics. I know this is a big scope. So for the work that I'm going to present in AIAA SciTech in 2 months, we'll just focus on this ML model retraining and also generating new data set for retraining this ULI network. This kind of approach is not totally new. Why? Because the data augmentation, like zooming out and zooming in and rotation, has been used for even like the OCR or character recognitions already. So I want to extend those work with this vision-based landing scenario. And there's a lot of future possible works. For example, if you can have a good state estimation, then maybe you can find the correlation of between state estimate, performance, uncertainties, and even safety. But those are very difficult problems. So, but as an initial start, I want to tackle a very simple problem. It's just retraining this ULI network using new data augmentation. And this retraining will happen in forms of this Bayesian optimization. So every iteration of flight in the simulation environment, and possibly sometimes I use this with the real environment with small drone, because the bigger drone is usually more risky. That's the work that I'm going to present in AIAA SciTech. Second use case that I want to introduce you is this. If we, this is actually the way to estimate uncertainties. You see this thin line box. As the dust level increase, you can see there's a thin line bounding box surrounding the solid lining box, bounding box size increase. This is just I scaled this size with the variance of the prediction from the 5 different models. You can demonstrate those increase of the uncertainties using this kind of game environment. And the work that I presented last year, only this year, was what if we use switch or gain schedule? This is switch here, but depending on the uncertainty estimate. The idea is that if we see uncertainty increase, then we can switch to a controller that has more focused on noise. So HMPG control with a greater weight on the noise is selected to deal with this uncertainty. With this simulation testing, I was able to see that some performance improvements. So we want to use this with the better simulation environment and also with real flight too. I'm going to just briefly tell you. So this work is just I'm telling it's here because to show that we work together, and also Ayush and Dr. Shah has been used this LiDAR sensor from Kala environment for their work. Okay, some immediate work that I'm going to do is I recently learned that NASA already disclosed some 3D models. Some 3D model was detailed when I checked it, and some were not. So maybe I need to request more detailed 3D model to NASA so that we can add this vehicle to Unreal Kala environment. Future update with this first phase simulation development is Unreal 5 is much better than Unreal 4 that I'm currently using. In Kala, they are going to use this Unreal 5. In fact, there is a development version of Unreal 5 is available. I'm going to test this so that we can use this very good graphic quality. Probably you have seen this similar things in Professor Evangelos and also Evangelos' presentation. Yes, so he showed the simulation environment that used this Unreal 5. Okay, second phase. From me, I'm more responsible in working with this Kala environment, and this was not a lot of work because Christos already have this 3D model for Mini Hawk in this public repository, and this repository includes all that complete software in the loop resources. So I use that to import this model in the Kala environment. And also, Christos software in the loop simulation environment is extended from the popular AudioPilot software. So what we are doing is basically replacing this flight year simulation with the Unreal Kala environment with this imported vehicle. As you can see, by adding this, you can get camera images, also LiDAR, although it is not visualized here from this Unreal Kala environment. The third phase is going to be, again, starting from this software in the loop simulation. Previously, this part was autopilot software runnable on desktop, but now we can use some popular autopilot hardware like Cube Orange or Pixar or other PixRaiser and all. And then we can use USB ports, and so that the software can be run on hardware computer. Furthermore, using mobile GPU like Kadas that is currently used in the Mini Hawk, and also all these different more expensive, more powerful NVIDIA Jetson device can be used for processing camera images, LiDAR from the Unreal Kala environment, so that this can be run as high-level decision maker, work with low-level controller and low-level estimator inside of this autopilot hardware. In addition to all that effort in UNR, in Tennessee Tech, I'm also building some VTOL vehicle. Its wingspan is 2.4 meters, so that it supports greater payload and greater space. Basically, this is RC glider plane, but we are adding this 4 propellers. All this kind of modification has been popular in hobbies or robotic community, so I'm sure that this will work. However, I ran into several crashes, summer and fall. We are upgrading the vehicle to add some more beam to have steeper frame. Why? Because unlike quadcopter, because this vehicle is large, so it get into strange structural oscillation, and that was the cause of several crashes. So we are doing this, and also we are designing some avionic carriers so that you can utilize the space inside. And furthermore, we are upgrading the propellers and motors and the battery to more higher end. We started with very cheap version of those. I believe that data sharing and software sharing is essential for collaboration and integration. Thankfully, Ayush, Dr. Lewis group, we initiated a good GitHub repository that replaced the old one that I used to minimally manage. The main contribution he made was he put everything into this Docker container, so all this software dependency issues is minimized. Also, Mikhail in Dr. Hubakin's group he actually developed this Docker container that runs this mini Hawk software in the loop simulation. And this is what I did. I published the simulation environment, the Kala app that has two vehicle as a Docker Hub images, so that you can use this command to pull these images from internet. Ayush started pushing toward to modular software structure using Docker Compose. So to illustrate why they are useful, you can run multiple containers as a software node with different OS and different Python environments, such as maybe Jax or the PyTorch. Maybe they are not compatible, or I don't know. And also you can run different versions of ROS. So, and furthermore, what Ayush did is he not only container modularization, he tried to make the folder level modularization. I think this will be really helpful for future collaboration. Thank you, Ayush, and all that contributor to this work. This is all I have, and I am getting some subcontract through Petrus. This is 2 students that I work for, and there's Duo who has been helping me with all this software integration with other groups, and 2 students from Petrus. This is it, and thank you.
Thank you, Hyungjin, and thank you, Petrus, for this wonderful presentation. Irene just posted one question. So Irene, if you can open up your mic and you can just ask a question.
Sure, thank you. So Hyungjin, maybe I missed that, so sorry. But will you be able to quantify how well Carla only training works versus some combination of Carla and real world training data?
I don't have really good solution to this. I will show to have some real flight and the color simulation together. I do not know what weight that I have to put to these 2 different data sets. So I would think that it is possible to use some scalar value evaluation for whatever cases and then use it in the optimization. It is possible, but putting some relevant weight between them is a different problem, another problem.
Got it. Well, I'm thinking something actually much simpler and more in terms of when you get a chance to flight test, that if you have one set of technologies trained strictly in a sim and you go to flight test and see how well or poorly it does versus something where you're training on a hybrid, right? I keep trying to run down this idea that robotics been pushing, that you can go directly from simulation to real world operations, and just try to quantify where we are in terms of aviation. Not that I'm advocating that, I just try to quantify what the state of the art is.
This is not really a direct answer to your question, but some alarming keyword since yesterday was scalability. And then I was looking into foundational model for time series and large model for time series. Looks like there's some ongoing effort. They want to have a model that can explain whatever time series. I do not know this is really scalable, but large language model at glance, nobody expected this going to be scalable, I guess. I need to learn more, but this is my feeling that I had about this scalability issues with the deep learning.
Got it. Thank you.
Thank you.
So we're going to move on as we're slightly behind the schedule. Andy, are you here with us?
I am here.
Awesome. Okay, so you can get started and we'll push your terminal time to 5 minutes. So you'll end, you can present as planned, no worries.
Okay, sounds good. Yeah, thanks everybody for having me. As always, I'm always interested and enjoy seeing what everybody else is up to. It's even beyond the regular checkups, it's just nice. So I'm Andy Smith. I'm a principal systems engineer from SNC. And we're working mostly with UNR towards the technology transfer. Just kind of the topics that we're going over today, a little bit kind of motivating the robust and resilient autonomy, especially the emphasis on the defense industry, which is what SNC primarily focuses on, though we do dabble in commercial as well. And then initially we were tasked with pushing a program towards or pushing our contributions towards the DVEP program, but we shifted away from that. So I'll just kind of briefly touch on what was achieved there and kind of where that wrapped up at the end of the beginning of year 2. And then really since then, the primary focus has been moving into the Volley 10 integration and testing. So the bulk of the content will be kind of be presented focused on that. So I'm sure as everybody's aware, robotics are really kind of having their moment kind of coming out, especially in the military. They're being widely used around the globe. And there's obviously mixed feelings on that, the way it's being used. And then some of the largest things impacting these systems, and it's also bleeding over into civilian sectors in areas adjacent to conflict or even on the civilian side where there's no conflict around. The GPS denied environments, which again has been mentioned multiple times today, where you cannot always count on having GPS. And then even frequently GPS won't have the accuracy needed to guide a ship, if you're talking 8 to 10 meters level accuracy. So you need additional sensing to be able to bring that in and then also be able to detect when your GPS is being compromised. Another big thing is moving towards more autonomous systems, so you don't have to rely entirely on a reliable communications link back to an operator, because those can also be disrupted. You need to make sure your system will continue to be safe even when the communications link goes down. Now, despite these kind of two requirements that are having, things are pushing ever more and more towards more unmanned systems or uncrewed systems. Sorry, I should update that. And then in the defense space, one of the big things to always kind of keep in mind is the enemy gets a vote. So as we're kind of watching in real time in Ukraine and Russia, jamming is continuously prevalent. It's a constant kind of conflict going down for denying GPS and comms and other pieces like that. So a lot of the issues that are being addressed here are definitely being used to provide safety for a lot of our soldiers overseas, as well as some of our allies overseas as well. And then deep learning does kind of obviously offers a lot of benefits that's being touched on again and again, but it's very difficult to kind of know what's going on there. So the work that's coming into that space to ensure these systems that are leveraging machine learning are actually safe, and we have ways to verify their performance, especially at runtime, is really critical. So as kind of mentioned briefly, SNC's emphasis is initially really focused on developing that photorealistic simulation, which seeing the other presentations, that's something that's widely being developed across the entire ULI team. So we've started initially with the DVEPS program focused on the helicopter, now transitioning over to the Volley, and then now taking some of those capabilities from simulation and then attempting to transitioning them to actually do flight tests primarily with UNR on the Volley 10. So here, just kind of the one slide, the DVEP system, just as a quick reminder, is really meant for pilots operating in degraded visual environments where they're basically flying into an environment where they get dusted out and they need to continue to operate safely. And then this is also this is highly relevant for autonomous platforms, military, as well as within the civilian space, where you need to have some quality assurance that you're going to be operating safely in some of these degraded conditions with radar and other pieces. So This is a little bit of a snippet from part of the early simulation development we developed, kind of flying in a simulated environment, simulating DVE, and then also in a wider environment, actually simulating flights over the Reno area. So as we kind of moved along this path and kind of watching where the team was going and having conversations with UNR and others on the team, we kind of went back and revisited some of the transitioning opportunities where we thought SNC could contribute best to this program. And SNC acquired a company called Valancy in 2023 that makes a range of vertical takeoff and landing UAS. And then this was really to support a few DoD efforts and as well as some emerging commercial opportunities. And this really seemed to align really well and provide a much simpler test case for the ULA team than trying to operate on a crewed Black Hawk, which can frequently be prohibitively expensive to get flight time on and other pieces like that, especially for technology that could potentially put the platform at risk. Comparatively to a UAV that SNC owns internally, it's a little bit easier to kind of push the boundaries a little bit. So this is the Vol-AT. This is the larger of the two birds. These are primarily located out of Bend, Oregon. They also are fairly expensive, so the initial intent is not to fly on these program. As you can see, it's very large, a 24-foot wingspan. Max takeoff weight can be up to 400 pounds. It can carry a 50-pound payload. And then there's also quite a bit of active work on this to increase all these numbers pretty significantly going on right now. Not quite ready to publicly release all that yet. But this is a very capable platform. And the nice thing is all the avionics and controls and the inner loops and those pieces were designed to be identical to the Volley-10 airframe. And this is a video of the Volley-10 being flown by my team here in Reno. This is actually the UNR team came to SNC's campus just a couple of weeks ago, and compared where we're actually flying, we're only a couple of miles actually apart from one another. So this is our UAV out there going, and we just did a bunch of kind of transition flights, but it's hard to tell from the video, but it has a 10-foot wingspan, so it's a pretty large aircraft, even for a simple test platform. Max takeoff weight is 55 pounds. That's mostly due to 107 restrictions to make sure we're compliant with FAA regulations. It can actually carry a fair amount more than that. Payload weight is again restricted by the FAA compliance, and then the endurance is 1.5 hours, and cruise speed is 49 knots. So right now we have 3 of these in the Sparks office. One we've taken out and flown. The second one we're getting ready to take out and fly. Third one needs a little bit more work to kind of going after some of the flight tests and other things. So very excited to kind of start bringing this in and seeing what other additional tests we can have with the team. So additionally, we have other test platforms as well. This is just kind of one example. It'll kind of come in why I'm bringing this up in just a second. So this is one of our hex rotors. It's fairly large. It's a 3.5-foot wingspan from tip to tip. Payload weight's 11 pounds, endurance about 45 minutes. And what's kind of neat about this is similarly, it has the same Pixhawk flight controller as the Volley-10. We also fly similar sensor packages on it, so it provides an even simpler and less expensive way to kind of go out and flight test some of the autonomy stacks. So this is kind of the Volley-10 test plan that we came up with. So initially, SNC is to deliver the simulation environment to UNR. You can kind of see a video of this image of the simulation environment up here. It's actually taken. One of the things that we really strive for was to not was to have it represent real world locations. So we're able to pull in data from Cesium or Google or Microsoft, Maxar, as well as others, to be able to have real world locations. So this is actually UNR's football field in the stadium. And that really kind of allows us to test some of the flights that we actually plan to have. And SNC has done that internally for some of our own events as well. The next step is kind of UNR and SNC collaborating to identify where the test locations will be and what the concept of operations or CONOP will be. So what exactly we're trying to demonstrate and how will those flights actually go to make sure we're moving in the same direction. We all kind of agree on the intent and that it's meeting the larger ULI intent. Next step, integrate UNR specific cameras into our test payloads and perform various data collections. Big piece of this is just really making sure the calibrations are tight. We have the right field of view. We're able to capture what UNR needs for the test flights they want to perform. And we're not us bringing our hardware into this is not complicating their effort any more than it already is with all the research they're already performing. Finally, step 4, test and simulation over a few selected locations with specified cameras. Initially, I think this will be done by the hex rotor, followed by the volley 10. And then this will be done for initially in simulation, validate the autonomy, perception, sensors, and control. Then moving on to the next step, testing on SNC's hex rotor, again, really just for safety and keeping the cost and risk down. And then finally moving on to testing on the volley 10 at the test location. And then kind of another benefit of taking this approach, similar to what was already mentioned with some of the other simulation efforts, is this also allow SNC and UNR to test different ConOps that are impractical in physical systems. And that could just be because the locations, it would be complicated to get FAA approval to do the flight tests there, or it could just be the sheer volume. This will allow us to do significantly more flight tests than we actually could do on hardware. So here's a kind of video simulation. Very simple block diagram on the top right, similar to, I might have stopped. Similar, we're not using Carla, but Carla is based on Unreal. We kind of were in between the transition from Unreal 4 to 5. Some of our programs are still on Unreal 4. Most have made it over to Unreal 5. We recently did our own internal IRAD for a different effort where we used a very similar autonomy stack to what's on the Volley 10 for one of our other platforms, or kind of a test analog for it, where we flew 4 UAVs. Initially, we tested in simulation, very similar to how we plan to do the testing simulation to flight test plan with UNR. With Pixox, we were able to there provide Mavlink commands for a variety of control methods, including the set of commands that UNR would like to use for Volley 10. So really a lot of this is going to be leveraging some of that previous internal research and development efforts SNC has done to account for their sensors, and then also kind of try to match the platform dynamics a little bit more. One thing that is nice about this, especially by providing the simulation to UNR as in advance, is they can use it to kind of evaluate what cameras they would want at different test locations and how, and in the specific ConOps that we're going to have, to kind of just verify before we spend too much time on the hardware testing side that things look like they should work, which kind of, as Irene pointed out earlier, it is kind of difficult to know where that simulation reality gap exactly is. But hopefully this can help narrow it and maybe be able to collect some data towards that. And then we did kind of switch over a model of just a VTOL on this point. Currently the sim is set up for either fixed wing or quadcopter, hexcopter mode. We're in the process of making that switch so we can kind of transition between the two. And the first step was, as Hyunjin also kind of hit on, is bringing in those models and making those work well, and then also bringing over the physics. So here is kind of the ConOp that we had discussed with UNR. And this is all tentative change. This is all fairly early. When you have, as I kind of went over, we have a little bit more work to do, kind of verifying this is the mission set that we want to show, that it best maximizes what UNR's algorithms and autonomy is able to do, and then also just kind of making sure the locations are suitable, the work with the sensors and other pieces we're kind of picking out. So this is potential change, but it should be fairly aligned to this general concept. So initially having some flight from Susanville, California to Reno, Nevada, which is about 75 miles apart. And then en route, there's effectively some type of emergency. And just for the sake of having locations that be suitable to fly, meeting all the requirements and other pieces, there would be some type of en route emergency near Doyle, California, requiring some type of improvised landing. And then again, this is all my understanding of UNR's autonomy, which Christos certainly understands better than I do. And fortunately, he's following me and hopefully he can correct any mistakes that I make. But they'll effectively scan for potential emergency landing locations. I've kind of identified them here. 3 was chosen by me just arbitrarily. Route is selected between the 3 and pushed to autopilot using Mavlink guide messages. So at this point, they'll basically fly across the 3 locations using message formats that we've already integrated. And then finally, each landing location is inspected. And then once a suitable landing location is found, transition over to Mavlink auto messages to put in the landing location. And there, Christos would be providing, or UNR would be providing to us a position in the UAV's local reference frame for where it should attempt to land. And then it would conduct the landing. For this, what we're kind of envisioning is it would kind of fly like a quarter cloverleaf, or effectively flies over the top of it, verifies that it's safe and suitable, and then goes in to actually perform the landing. Here's kind of what the Volley-10 hardware diagram looks like. Kind of review this with UNRs, make sure all the pieces fit. Kind of all the various components you would expect. So PICSOC, NVIDIA Orin NX, and then all the ESCs, motors, and sensors. And then these would be ULI specific sensors feeding into the NVIDIA Orin NX to guide their stuff. And then UNR's code would be hosted on the NVIDIA Orin NX, putting out the Mavlink messages digested by the PICSOC, and then sent out to control the platform. We currently have two kind of vision modules that we're open to using for this effort, but I think ultimately we're going to collaborate with UNR to kind of come up with a custom one. I'm already having discussions with Christos. So the first one has a bunch of EO cameras, as well as the INS, the VectorNav VN200, and NVIDIA Orin NX. We've flown this since about 20 November for about a year now. And then we have another one with long wave infrared camera, so a few FLIR bosons. Again, VN200's NVIDIA Orin AGX on this one. In this one, we've only been flying for a couple of months now, actually. But ultimately, I think there's going to have to be a discussion of what cameras exactly we should have, and what kind of modality, whether they want LWIR or EO cameras. And I also think there's going to be some combination of focal lengths and orientations as well. As far as doing the actual integration, a big part of this is kind of ensuring the safety of the platform as we're performing the various tests. And there, SNC is going to integrate kind of a safety check over the commands coming out of the UNR's kind of autonomy stack. So there's effectively two ways that we've internally discussed going about this. The first one would be we simply intercept all the Mavlink messages, almost like a man-in-the-middle attack, and basically inspect them, compare them against some of the prior data we have on the flight safety of the platform, as well as the environment that we're operating in, to ensure that nothing's being done. And then the messages that are believed to be safe will be passed on to PICSOC. Otherwise, we'll put in some other command that we believe to be safe. And then the PICSOC will execute those commands at that point. The other option in this space is ArduPilot already has multiple kind of plugins or accessories you can have to basically to kind of enforce this inside the PICSOC. So at this point, SNC would be doing something a little bit differently. We would actually allow the ULI autonomy stack to interact directly with the PICSOC, providing here again the guide commands. And then SNC would be either a priori prior to the mission beginning, or potentially in real time, depending on exactly what the ConOp looks like, going in and modifying some of the data sets. So the way that these two safety checks works, apologize, probably should explain that first. The first one is an ADS-B, where it basically gets the position of potential other aircraft operating within the vicinity, and then mitigate deconflicts to ensure that there's not a collision. Basically puts a bounded area around it and refuses to enter inside that bounded space. The other one is terrain avoidance, where you provided a similar to a DTED map, effectively an elevation map of the area that you're operating in. So we could go, and anything that we believe that is moving, we could provide real-time updates into the PICSOC or the ArduPilot as an ADS-B message, which from recollection, I believe it can handle, I think it's 255 different ADS-B targets at one time. And then on the terrain avoidance, and then anything that we know that is static that we want to avoid, we can simply modify the DTED data that we're uploading before the mission begins. So there's a little bit of flexibility there. There's still kind of internal discussion on which of those two routes we really want to go, which one we think will induce the least lag and still provide the best capability to exercise the autonomy UNR is developing. As we kind of mentioned before, one of the big pieces of this is really going to be integration within the simulation environment. So as we started talking about how we would integrate this into the aircraft, one of the big pieces was ensuring that we actually integrate into the simulation first. The simulation environment right now already ingests MAVLink messages. So it'd be fairly simple to take the autonomy stack that's being developed, output the MAVLink messages in the right point, and then duplicate the behavior that's happening inside the simulation environment, and then use that to generate the simulated sensor feeds, either cameras or INS, LiDAR, whatever additional sensors UNR or anyone else in the team happens to need, as well as simulating the physics of the platform as it moves through the environment. It's actually remarkably similar to Hugh Jin's presentation he just gave. I actually like his graphic he did a little bit better, so I applaud him on that. And then this would operate effectively the same way for either the either way that we do the simulation check. And then this would, of course, be applied identically to either the hex rotor that we would test fly initially, and then also the volley 10 as well. So kind of revisiting the volley test plan. So initially the plan was deliver the simulation environment to UNR. We've done that. It's running on their machines locally at that location. In work, collaborating with UNR to identify the test locations and kind of hone in on the ConOp, kind of ran through exactly what that would look like. And then the kind of next steps are also kind of in work is starting to discuss with Christos what cameras and what the test payloads would look like. So S&C can leverage either the hex rotor or the volley 10 and go out and perform some data collections to verify that the cameras that he would like us to use will actually meet his requirements. And then, of course, going out and doing recreating the missions or the ConOps inside the simulation environment, and then fleshing out the full autonomy stack, both software in the loop and hardware in the loop testing, and then moving on to performing the actual flight tests. So on a S&C hex rotor, followed by the volley 10. And then, again, of course, going through and doing additional simulated tests that might not be practical in the physical system. And then I apologize, I went through this significantly faster than I had intended, so I got a little bit of time back. But again, so to kind of summarize, S&C simulation environment was been adopted from the original DevEps platform over to the volley. And then we really kind of shifted some of our internal development plans on the volley to support this effort, with really the intent there of demonstrating a portion of UNR's autonomy demo. Of course, they still have other platforms and other partners they're working with, but we are shifting some of our internal planning to really accommodate and really try and do as much as we can to work with UNR to put their autonomy stack onto our platforms as part of the demonstration. And then with that, like I say, first, I'm sorry, I went through that significantly faster than I had intended to. But I would like to say I'm kind of thankful for the attention. And as always, I'm really just kind of grateful to have the opportunity to be part of this team, and happy to kind of open up to a discussion or take any questions.
Thank you, Andy, for the wonderful talk and the nice looking videos. So any question for Andy? We only have time for one question at this moment. But after Christo's presentation next, we have 20 minutes dedicated time for discussion of integration and demo plans. So if we cannot finish the Q&A in this brief 1 or 2 minutes, we can shift the discussion there. Andy, there's one question from Chad from Sion. Can you read and answer that question?
Yeah, of course. So question, thanks for the presentation. I know the S&C simulator is being used by some members of the UL team. Are they available more broadly for academia? So currently we are not able to release it publicly outside of the ULI team. That is something I'm really working towards doing. Just defense contractors specifically really kind of struggle to push things out like that. It is something I would very much like to do, though. In general, I would like to be, I'm trying to move S&C internally and having some luck. with freeing some of the data we have that's not sensitive and or classified, and being able to share it and make it available to people in academia. So currently I cannot share it beyond the team, but it's something I'm working to doing. There was another question. Chang, would you like me to take that in chat so you can kind of move on to the next presentation?
Yep. If you can answer it shortly and briefly, and you can always continue this answer in the chat if you want.
Okay. So the question was, is there a test plan document we can review, being prepared to outline, what is going to be done? Not more formally than what I just presented. Sorry. That's something we're still kind of working on and refining. As soon as we have it, we'll share with the team.
Great, thank you. So we can move on to the next speaker. We have Christos, I believe. And Christos, you can start sharing your screen.
Yes, thank you. Sorry, it's midterm day tomorrow and email is going crazy. Share content. Can you see my screen?
Yes, we're looking at the editing screen. Can you make it to the presenter
Yes.
screen?
Just a second.
Okay, works now.
All right. Showed up at a different monitor for me, but okay. All right. First of all, thank you and for the opportunity to present our work. And I am Christos Papachristos, assistant professor here at the Department of Computer Science and Engineering. And this is the work that we've been doing towards the progress for systems integration and field deployment and verification. As Melchior mentioned, it's nice to follow up after people that set the stage for the technical challenge and what its purpose is. And of course, here we do not have as cool stuff to show in terms of math, like with Riemannian differential geometry, etc. But we have cool videos, which is always nice to have as a kind of closing presentation. So the work that we've been doing all this time is related to establishing technologies that are going to facilitate deploying the learning-based algorithms that are being developed as part of this ULI group on board the real vehicles that are to scale with things that can be deployed within the Nevada testing site and the regulations that we have to follow for the airspace here. And this relates to various different aerial vehicles that have different types of mobility capabilities, different types of payload capabilities, different types of endurances, and of course different types of mission specific operational capabilities, as we're going to be seeing further on. But the main feature that we're developing all things around is to be able to do systematic mission execution around the environments of the northern Nevada deserts and the types of landmarks and types of settings that are around the area over here. In the first year, we've been showcasing various developments that transfer over to capabilities of the aircraft as we integrate and build towards the types of aerial mobility vehicles that are going to facilitate the deployment of our pipelines. And of course, we have reached here the critical point of having to prepare for full integration of certain pipelines in order to be able to demonstrate them for the main mission. So at this point, I would just like to elaborate a little bit on the types of vehicles that the types of systems that have been developed and their capabilities, their operational capabilities, but also compute-wise and sensing-wise capabilities, because they've been mentioned systematically over this ULI annual review. You've been hearing the platform Minihawk quite an amount of times over the presentations. It's kind of like a unifying platform architecture, but also a physical platform that we have shared with UIUC, and they have their own Minihawk there that they can test as well. So it's kind of like the platform of choice for many of the ULI deployment capabilities that we target. So the Minihawk is a small scale. It's a self-sustainable aerial system in its conception. So it has solar panels and harvesting hardware custom designed such that it can self-hibernate. And we've gone over the idea of a sustainable mission over 2 consecutive days in the deserts of Northern Nevada, which is something that we showcased in last year's videos. The fundamental platform, however, is a tilt-rotor mini-scale aircraft that can carry payloads that consist of visual inertial odometry sensors integrated on a chip. So the idea here is to not have to spend computational resources in order to do visual inertial odometry in case we lose GPS, in order to support these GPS denied operations, which are always critical in terms of autonomy. The standard GPS and cameras, regular USB cameras that are used in order to be able to do image-based classification detection of conditions in the field that relate to certain operations that we wish to target. The autopilot is Pixhawk-based hardware, and the autopilot stack is the one that we deploy on top of it. The high-level computer is ARM-based multi-core, and the integrated neural processing unit is where we deploy architectures like deep learning-based convolutional neural networks to support some learning-based capabilities, real-time executed in the field. Again, this is a small footprint platform, which means even if we end up using a hybrid flight envelope, so fixed wing as well as vertical takeoff and landing, it doesn't make it past the 10-minute mark in terms of endurance, but it is sufficient in order to demonstrate the mission capabilities that we are currently pursuing to be able to demonstrate in the field, also as part of the field demonstrations in the for this NASA ULI third year. The progress that we've been making in terms of the capabilities of the Minihawk is not just in relation to the systems development and integrating the deep learning capabilities on the aircraft for real-time execution, but it also relates to providing models for Evangelos system in order to be able to design the MPPT-based control in order to be able to do covariance steering-based landing, for example, which is one of the target deployment capabilities that we want to have by May demos. And we've, of course, demonstrated that it's possible, as you see in the video below, in prior work, that it is possible to detect terrain landmarks as landing zones, etc. But the next step is not just to do visual surveying-based guidance towards a certain waypoint on the map based on vision alone, which is something that we have established, but to do it safely, utilizing something like a covariance steering-based control policy. So this is the type of integration and collaborative work that we are doing together with Georgia Tech's team, and we're actively pursuing and working towards getting a fully integrated covariant steering-based control framework on the Mini-Hawk. Then I want to introduce a different type of platform that is also available and has been utilized here for somewhat different purpose with respect to deploying learning-based technologies. It's a larger, and I will elaborate what I mean about somewhat different learning-based technology. It is a heavier payload system, standard hexacopter frame. It's specifically the M600. Higher flight endurance, of course, all of that depends on the payload, can carry lidars, etc. You've seen similar aircraft out in the field, and the way that we've leveraged this is in order to one important thing, it doesn't carry just a neural processing unit, it carries and Jetson or an NX from NVIDIA, which is a computer that's that has an ARM-based 8-core CPU, but most importantly, it has an NVIDIA Ampere GPU with CUDA cores, tensor cores, all the nice things that come with that with respect to deploying learning neural network-based policies in the field. I believe it's the same device if it's the 16 gigabyte version as SNC's payload, which is nice in terms of integrating and working on similar platforms. But the way that it's been utilized is with respect to, at least initially utilized, is with respect to a different project that has to do with fire-based characterization of the landscapes around Northern Nevada. This is a real-world field test, meaning all of that stuff has been systematically accomplished here in the area, and which is the same area that you'll be seeing during the May demos. But the most important thing is what you're seeing in terms of semantic segmentation capability deployed in the field. Of course, what we aim to do here is to demonstrate that we are capable of detecting even the microfoliage, microstructures on the leaves of sagebrush that can help us identify different types of sagebrush in the field, because every different species of sagebrush has different fire fuel and with respect to its mapping. But this type of capability of doing semantic segmentation and not just bounding box based classification and detection of terrain landmarks for landing is something that ties with plans to be able to detect not just very concretely specified landing zone landmarks, but areas in the underlying terrain map that are more unstructured but have a particular class type that lends itself to landing. And then this is going to tie with the presented next system, which is capable of doing landing on water bodies and not just helipads or football fields or building rooftops or whatever. It's capable of doing landing on water bodies, and as we know, of course, water bodies is not just something that's very concretely defined. Lakes do look differently than rivers. All lakes do look different from one another depending on how far high up you're flying, etc. Different shapes, etc. This system, let me dedicate a few minutes to describe the capabilities of this system. It's a mid-scale, amphibious, as we call it, migratory self-sustainable aerial system. The purpose of the system is to be able to cross the Pacific Ocean and arrive at Hawaii by doing multi-hop flights, but that's our eventual goal. It follows the same principle of integrating power management for solar power harvesting and all that stuff and self-hibernation capabilities, but as the Minihawk does, but it's also amphibious, so it's built to be survivable for long-term immersion in water. There's a watertight container that integrates all the electronics that you see here, such that it can remain inundated in water for prolonged periods of time. Of course, this is something that's a requirement if it needs to spend time landed on water bodies in order to self-recharge and take off again and do hop by hop an entire very long-term mission. So the nicer aspects of that is that it carries a higher-powered ARM-based computer with a more powerful neural processing unit, and of course the main feature is the ability to remain amphibiously immersed in water. The capabilities that we transfer over from this is to be able to demonstrate medium footprint evaluation of the learning-based autonomy components. So whatever the Minihawk can do, this can do, and also have a higher payload capabilities to integrate. But the most important thing is, again, the ability to sustain demonstrations that involve emergency landing procedures that involve water. This is not just one of the this is just one of the capabilities, however, that we consider relevant to the ULI project, because the other important aspect is that we have deployed deep learning models that deal not with just terrain landmarks, but also with the visual appearance of specific environmental phenomena settings that are considered to be high risk. For example, here we are showcasing the left slide. This is during a recent mission that we did. The appearance of a wildfire locally in the area around the lake that we were flying, which is something that can be detected with the onboard camera and the neural processing unit on board the aircraft. Of course, the next question is, then the next goal for us is to be able to deploy this semantic segmentation, the previously demonstrated semantic segmentation approach, which can be deployed on board a heavy payload, which is and heavier in terms of of power requirements. NVIDIA platform, to be able to transfer that over to a neural processing unit in terms of capabilities, or at least to some extent. What you see on the right side is, and the reason for doing semantic segmentation, again, is to be able to, as you fly by, to pick out an area for safe landing based on its appearance, and its appearance can be that it's just a puddle of water, for example, and it's not something that can be very clearly defined and trained for in the regular sense of just being a well-known, well-structured terrain landmarks with specific features. For example, like football fields, which is the example that was demonstrated in the earlier slides. The right-hand side was a video related to survivability and resilience of this platform. As you noted, it's possible that if it lands upside down, like flipped over by a wave or whatever, it's capable of self-righting, as we say, and also it can do flight with higher efficiency control by staying close to the surface of the water by leveraging surface effect, etc. These are things that we have demonstrated in the broader sense of operational capabilities for such an aircraft. But the most impressive aspects, of course, the field deployment, the real-world field deployment of this aircraft within the context of long-term missions around the area here. So what you see here is the actual location that we ran a 3-day mission cycle with this aircraft. You see the wildfire, of the wildfire on image frames. And what you what is being demonstrated here is that this amphibious platform can self-sustain and do multi-day missions in the field. Now, how this relates to the NASA ULI project, first of all, it relates to being able to systematically, repeatably test mission cycles that involve edge cases that can be mission landings, triggered mission landings due to simulated faults around areas that have water bodies and picking those locations to land on, and whether it be through vertical takeoff and landing or with gliding type fixed wing landing on water bodies, which is something that was demonstrated in the previous video, and the broader repeatability testing for the architectures as a whole that we develop, and the fact that they remain resilient for these types of systematic testing that we want to have for the deployed algorithms. And the last thing is, of course, the coolness factor of demonstrating such a thing with an aircraft that would, have uninterrupted, unintervention operation, no operator going out to tend to its needs, swap out a battery or anything like that. It's just capable of taking off on its own, self-recharging, etc. All those things in the field, and this is part of what we intend to demonstrate for the scheduled May demonstrations. All right, so from my part, that is, I think this is all. This is just a very long video because it's 3 days of testing and the recharging cycles and all of that stuff. So I will just skip to the end of the third day. And this brings me to the end of the presentation. I would therefore like to thank you for your attention, and if you have any questions, by the way, all those videos except the last one, which is work submitted to this year's ICRA, hopefully it will get accepted. All of those videos are published on the Robotic Workers Lab website, and they are publicly accessible if anybody wants to take a look at our work in this medium. So thank you, and I'd love to take any questions if there are any.
Thank you, Christos. We actually have the demo-related discussion after your presentation, so we can maybe take this as an extended Q&A, both regarding your talk as well as the questions people have in general regarding our demo plans.
Yes, we can jump directly to demo-related discussions.
Okay, let's see what the audience
will say. Are there
say.
Questions here for me on the chat? I see there have been some. Is there a test plan document that we can review being prepared to outline what is going to be done? I think we have prepared something like that together with the UNR side of things and SNC. And we have submitted that to ULI leadership, and it should be something that is either under preparation, it has already been finalized. I don't know if it's available at the moment.
It would be good, this is Kevin, it'd be good to see like, okay, what are the software components that are coming from the various TCs, how they're being integrated, how whatever the TC was on the V&V stuff using Verse and so forth, how we are, V&V learning-based components, and then how they're being integrated, and then what the demos are going to be that show that this stuff works.
Yes, I think
nice
this
to see that kind of written down. Like, there's been lots of development in the last couple of years, right? So I'm not sure that I have a good grasp of how all the TCs are contributing to the autonomy stack, what components are going to be actually integrated at Reno and then tested.
Yeah, so from my side, I think this is going to be answered more in the discussion, and hopefully somebody else can jump in and just leave me to answer the whole thing on my own. As far as I am aware, the most intensive effort that we have right now for field demonstration, integrated field demonstrations, is the integration effort with Evangelos's MPPI based control for covariant steering based landing.
Yeah, maybe
For the
I
May
can
demo
add something
specifically.
to that.
Yes.
Yeah. Thanks, Christos, and thanks for the question, Kevin. This is Shayan. Yeah, so we have had a number of conversations with Christos and Petros about how we could apply verification and testing to this platform, and several ideas are sort of simmering, and we haven't quite converged on which one makes the most sense or which ones we will implement in the next year. So I'll just share with you some of the ideas that we have talked about. So one could be checking that indeed this emergency landing kind of scenario using verification. So there is a mission that the Mini Hawk is flying, and then something goes wrong, and there has to be like an emergency landing, and that kicks in some recovery maneuver at the logic level, and then through reachability analysis, we could try to say whether that recovery process is safe or not. We could also try to do collision avoidance, like the stuff I talked about yesterday, either multiple intruders or a single intruder, with or without availability of the prediction of the intruder's trajectory. The Mini Hawk or one of these platforms could be running an ACAS type protocol to do collision avoidance, to evaluate different avoidance procedures. That's also something that could be checked. Now,
so
these checks,
in the emergency landing scenario, so where are the vision-based landing? I get that, but where are the learning components in that software stack?
Yeah, so what we have discussed so far is like vision-based. So maybe it's a football field or a clean sort of area that the vision system is able to identify and guide the aircraft towards that.
No, but where are the learning components in the software that were trained? Where are the neural networks that you're using? How were they trained, and how were they V&V'd with Verse or whatever the tools are that are being developed by that TC? Am I making my question clear?
Yeah. So so the one way to do that is some things we talked about last time and only in passing this time. So you could have like a vision-based landing system so the neural networks are in the perception part, which is picking up, let's say, key points on a football field to give pose estimates to the rest of the control pipeline. Now, how do you verify that neural network? That's a separate question. And one of the ideas is to construct these over approximations of the neural network through what we are calling perception contracts. So then you are not directly verifying the closed loop system with the neural network. First, you are constructing an over approximation, and then you are verifying the closed loop system with the over approximation. So one could approach it. So that's one of the approach. Completely verifying an end-to-end system where the neural network is doing perception. That's also something we have looked at, and there's a scalability question, and perhaps that's the second approach we can try.
Okay, thank you.
Any other questions from the audience regarding the demo plans that we have fully reviewed so far?
So I'm not sure so much as a question, but I think more of a comment following on what Kevin has been emphasizing over the past couple of days. And I think it's going to be, once we have a better idea what is actually possible to demonstrate, and I suspect that may happen within the next month or so, a detailed plan of what is being demonstrated, including, you know, the nitty-gritty of details, what's going where, and what kind of assurance methods, i.e. V&V methods, can and will be applied. And clearly it's not going to get end to end, right? Or maybe it will, but what is it that is verifiable? What is not? How is it done? You know, what would, if you had more time and or resources, you could have done X, but you know, and some things are completely unknown. It's still completely open research question. I think that would be a worthwhile document to start and to keep. Is that a fair?
Yeah, very good, Irene. It's not that I'm not trying to get people to write a big document here or anything. It can even be a PowerPoint summary of, you know, just how things are being integrated, but you summed it up correctly in terms of where I've been probing. Yeah.
So Irene and Kevin, we actually have collected this, what we call one pager for the demo plan before we're getting to the review, so that internally we have an idea of what's to be planned for the demo and what we're gonna demonstrate in those demonstrations. So, but it happened probably a month ago, and maybe we didn't get time to collect your feedback. But the points you raised are valuable for us to, you know, do or expand our one pager to give more details regarding, you know, the demos we're going to do.
Yeah, because, you know, after our last meeting, you know, a conversation I had with Richard, and I put together what I consider to be a functional architecture diagram of a civil UAS, and where my opinion, where I think learning components would reside. And, you know, so from a very top level perspective, you know, I think this program is trying to close the gap in the use of this technology in these applications, and certification of these components is a huge challenge for everyone. And so I'm just wanting to make sure that we can point towards that, saying, okay, here's what we've done, here's the components, here's how we could or have certified them. I understand there could be a resource challenge there because this might be beyond the scope of what was funded, and then, you know, so if I was to take this, you know, take a summary of this to WISC or to, you know, the autonomy leadership here at Boeing, you know, I'd like to say, look, here's what they're going to demonstrate in Reno. Here's why we care about it. Yeah. Now, you know, I know Evangelos's work with covariance-based steering, great. I don't see that transitioning into Boeing products in the near term, but some of the techniques for V&Ving learning components, particularly in perception, would be very valuable to be able to transition into projects here. So that's kind of the greedy side of my questioning.
If I may add, just a comment, Kevin, just everybody. There's been quite a bit of work that's been going on the different committees and regulatory side, trying to figure out a roadmap for AI certification. So I think FIA just published something. They're holding workshops. There's other things. A colleague of mine, Dr. Niyogi, has been involved in a lot of that work, and so I think I would suggest that may be useful is invite her as one of the sorry, the monthly seminars, specifically focused on sort of what's the latest thinking, right? And that may better inform how we talk about it, because sometimes it's not just the techniques, it's how we talk about the technologies. And she perhaps can provide a little bit of a different perspective and help us trying to formulate sort of a more cogent approach to what Kevin is after. And not only that, to penetrate into the regulatory environment. And frankly, I think this is Irene's personal here. This is my personal opinion, is that what's going to happen is that the way we regulate things will have to change, because certain guarantees that regulators think they have now. I'll give you an example: gain and phase margins, right, for a control system, will not be those guarantees. Those be probably something that looks different. But they need to understand what can and cannot be said, and what does and does not work to keep providing that safe aviation system. So that's, as I said, it might be worthwhile to have that conversation. So that's just my 2 cents.
Yep.
Well, I might also say here that, as I said in my early slides, that this month, November, I mean, we're going to narrow down more details on what we want to do and can do. And so that might help in, cleaning up this document and, that Kevin and you're talking about, which makes a lot of sense.
So it doesn't really need to be a formal document. Give me the elevator speech that I'm going to give to an executive that tells them what was accomplished here in closing the gap on using learning components in safety critical systems. Just give me that. Tell me where the golden, bolts are that we've created here. This is great technology development that's going on here. It's definitely, raising, addressing very important issues, but let's see. So my perspective from this program is we still need to be able to certify these things. And I want the thought leaders that are involved in this ULI to help guide us in how we do that, right? So that'll just be one of the comments that I write up tomorrow. So we're just kind of having the conversation today, but for those of you that,
Sorry,
go ahead.
Go ahead.
I was just going to say that, emergency landings, a single engine jet aircraft, we have a number of autonomous algorithms that do emergency landings for those kinds of aircraft. They've been in use for a long time. Now, vision-based steering is still new. So I think this is a very good thing to be planning here. So, yeah. And then, like I mentioned just a minute ago, any learning components that are used in perception, how we train, how it was trained, how it was verified, that process is still trying to be negotiated, like Irene said, in these committees on what are the artifacts that we have to produce for certification. And so industry doesn't know this yet. We don't know, and we're still, I think really the FAA kind of wants you to put it out there and then they'll see if they like it.
Yep.
That's kind of the story, right?
Bring me a rock. I'll decide whether I like the rock or not. I mean, no kidding. They're asking, in a lot of cases, they're asking us what should be the artifacts. So that's, and this is an opportunity to actually influence that. I have a quick logistics question, Petros. Will we be able to pretty quickly narrow down the dates for the demos so we can get the, send them out and the committee can block out the time?
Yeah, I think it's more up to you to decide. There are two windows. I think that from what I have felt is that people might like more the late May date, window. So whatever is convenient for you and the advisory board in these two windows is fine with me. I can do it quickly next week if you like.
Yeah, the sooner we can try to get this plan out, the better, because I'll just say May is a busy month for a lot of us, and make sure we can fit these things into our schedules would be great. I want to make sure I can attend some of these activities that are in Reno. Yeah.
Sure.
So Kevin, why don't we put that as part of the, why don't you put that as part of the discussion tomorrow for those who will be available from the panel, then we can send out, I'll send out an email for those who are not available in person, and that way we can narrow it down. That would be great.
So this is a general question, not related to this. So how well does this team feel the TCs have interacted? Are you all just pretty much doing your own thing and now we're going to bring things together? Or has there been significant interaction based on how algorithms work and how they would integrate into an autonomy stack?
From my perspective, I've been a part of several big projects. The interactions have been pretty strong here, right? So we have these weekly seminars that most of us attend. There are also sort of weekly meetings for certain subgroups where we really try to thrash out how we could do things differently, learn about each other's technology. And then sometimes some of these subgroup meetings fizzle out, or we decide that, oh, this is not the right time to build something together. We will revisit it when we have solved XYZ problems which are in the critical path, right? But there is no lack of, I would say, interaction that is blocking us from making progress.
Oh, no. So the reason why I asked that question is we've had programs here at Boeing where I'll just say mission systems have showed up with interface to their software that the rest of the program didn't understand. And last minute, I'll just say these interfaces didn't connect up correctly, right? And caused rework and things like that. So I was just wondering how well that's worked here.
Yeah, maybe one thing I would like to say in anticipation of this demo, maybe just to set expectations a little bit. So there is the cool field demos that Christos talked about, but so what some of us are working on are these design methods or verification methods, right? Which are not things that happen in real time. These are techniques or artifacts that you generate while you're designing or analyzing the system. So I just want to sort of make it clear that demo for this will not be like a real-time thing that happens. We will show how you run the software, what comes out of the analysis, what counterexamples come out, and how we learned about the model and how the machine learning models were trained, etc. So all of that can be demonstrated, but it's not necessarily going to be, oh, an airplane is flying and we are sort of doing some runtime verification of that. That second thing is also possible, right? We could run reachability in real time to do some conflict avoidance and so forth. But that's not the only way where verification is demonstrated. Just wanted to say that.
I was thinking along the lines of, the failure detection stuff that was briefed earlier this morning. Is that work being focused on the vehicles that are being planned, being flown at Reno, so that we're actually going to, this is how you were choreographing the experiment? Are you actually going to introduce a failure on the vehicle, like a loss of a rotor that could be commanded from a remotely, and then watch the system operate under, no kidding, a real failure? Or we're just going to do a vision-based landing as an emergency, as if a failure happened? That's not quite the same thing, right? So that's why that's kind of this document that talks about what we're going to, what components are actually going to be put into the software stack, and how were they developed for this flight test, and then how they were V&V'd, and then we go off and do it, and it all works, and then we wave a flag that says hooray. Right.
It's all in progress, Kevin. If you join our weekly meetings, you'll see that all these issues are being discussed. Today, we can't say whether we will have the actual failure and get rid of it, or it will be simulated. So this is all work in progress. And like Cheyenne said, we have weekly meetings, bi-weekly meetings between different trusts and team members. So things are moving forward.
Well, see, I don't think I have bandwidth to attend weekly meetings with you guys, but all the things that you've developed here are new, and it'll be a good story to just make sure we do a good plan. That's really what my questions are probing, that we have a good plan to bring these components together and talk about how they could be certified. First of all, they need to work, or why would you even use this approach? So maybe that's just the part that you're proving right now, is that this algorithm actually does work, versus, if you have such an algorithm, how do you certify it?
Kevin, in an ideal world, we would have loved to see everything coming together on a pre-specified platform from NASA, like it was in case of AirStar, and going and flying. But in this case, we don't have a platform hardware from NASA to go and fly. Instead, we have the Guam model. So like Cheyenne said, certain things will be demonstrated on the Guam model. Christos has platforms that we can go and fly. What can we bring to a platform for which there are lots of black boxes? We are limited. This is like we were flying the Rascal MPS that had the Piccolo black box autopilot. We couldn't do much there. So there are limitations we have to live with, because this is not like AirStar experience for us. And we learn it every day. Questions you are asking are very good questions, very valid questions. We know about it. We ask these questions, but we understand our limitations. So a $6 million program for 3 years for this team. This is how far we were able to bring it. To say we slept few days, didn't work, would be wrong. Did we always pick the right solutions, the right strategies? Lots of things we learn on the go. And because in academia, the joy is in the discovery of new things, you just can't resist people's passion to explore new ideas that come up in this process, that are not directly related to a particular demo or a particular V&V. This is academia. So this is how far we were able to push, and thanks to everyone's effort towards integration and building all this. I think if NASA goes and finds funding for another 2 years, then all your questions will be better answered than today or even in May. That's my conclusion.
Yeah, very good. That's a good response. I mean, let's see, I'm not trying to be critical or anything. I just would like to see a summary so I can better understand. Now, I can try to go through the charts myself, but it's better if you guys do that for me, I think. Right. So.
Yeah. I mean, let's be honest, right? We are in academia. We're not in a jail to say, this is the project, this is what we have to do. We have to get it out. That was the case with AirStar. But here, there is lots of freedom. Thanks to NASA for giving us Guam. Thanks to Christos for putting this mini hawk. And everything else that's happening around all of us, given all our other projects. the ideas that come up and go. Academia is a different place. That's all I can say. And you just have let people flourish, do their best what they can. And altogether we are advancing the science of autonomy with certain validations, demos, proofs, excitement, students, outreach, everything together. That's what this project is producing, moving forward. I don't know, I'm very excited by the team and by everyone's commitment to openly share what they have, to get onto these weekly meetings with all their schedules, because everyone is excited to see what's coming out.
So
and
just as
to
a
end answers, you don't seek in academia. Here, everything has to be open-end.
So just as a comment for the community here, so we're having a conversation, the detect and avoid, in collision avoidance area, I think is one of the first really big needs in industry. I think, the companies like Whisk and other companies that are developing these air taxis, they're looking for some solutions to help in the development of detect and avoid. How would you, so I just throw that out there. That's a really big area right now that I hear in all the meetings with
You can
focus,
say, make this demo, detect and avoid. And we have here algorithms coming from Boli, Evangelos, and Cyan. We are doing this vision-based landing. We can add one type of element like what you are suggesting and test how these new algorithms will prove themselves in this particular context. That's a valid question to ask. You can say, okay, show me this demo, and we can go and work on that particular demo.
Yeah.
But you have to understand that this is not going to be a Boeing airplane. This is going to be the Mini Hawk. This is going to be.
Oh, no, I understand. So we've had a lot of work in Australia using the Scan Eagle, and for that particular vehicle, but I'll just say that the sensors that are being used are so platform centric. The sensors that would be used on a 40-pound UAV isn't the same thing that would be used in Whisk, right? And I know that the whole training approach and perception and image processing, track file management, all the things that a detect and avoid system would have to bring to the table is going to be very platform tailored to the platform. Yeah, so I know we have those challenges, but just like you said, though, if you posed this kind of a demo, like a detect and avoid demo, what components were developed that could be brought to the table, and maybe this is for some follow-on work that NASA could potentially fund, would be, how you do this. Now, also, there's some other ULIs in this area, and maybe that's something for Irene to comment on, is how does NASA plan to do the next phase, or is there a next phase of just into place somehow?
So I can comment on that, unless there's somebody directly from the program office. Going once, going twice, no. So to the best of my knowledge, NASA is not planning on sort of collecting the best and then taking it further to mature as a technology. Not officially, not directly. So I have been trying to do so in the little, slice of the world of NASA that I have some impact and influence on. And we certainly are planning on trying to do so, again, in vehicles that are considered to be representative and provide relevant environment for these UAM class vehicles, right? So that's sort of Irene's answer to that. But I think I just want to make a comment on one of the things that the team has worked pretty hard on, and it's something that we've been trying to emphasize, is that all of this different work and all of these different algorithms, it's all fantastic. And you've seen it the first year, people are applying it on platforms or simulations that they had access to. And I think it's very important to apply it to a common platform, to a common simulation. And sometimes it's platforms because you have that. Sometimes you may not be ready for flight, or frankly, the platform may not be able to do the kinds of experiments that you want to do, either because they're too risky or just because the integration would take too long and you don't have the resources. So here comes that simulation environment, right? But ideally, you have exploration of what are the algorithms capable of doing, not only under nominal conditions, but with a bunch of more complex iterative failures, different sensors, different data processing techniques, all of that can, V&V, all of that can certainly be worked on by the group on a common platform. And that's what we've been sort of pushing. Hopefully that starts answering certain questions. There might be some things that you find that algorithms are limited to, and that may not be the right approach. There are others that might become promising and you want to take it to further development. And hopefully that is what's going to come out of these 3 years, with certain things identified as perhaps this is what should be further developed for that next set of technology maturation. And here's areas where there's still open questions that really need to be explored still in the more academic world. To me, that would be a big win because it kind of sets that baseline of where we are and where we're going. Also, I think one way to help that, and I think it would reflect, Kevin, a little bit of some of the questions that industry has, is benchmark problems, right? If we, hopefully we started, but there's a lot more work to do in formulating benchmark problems under real world assumptions. And then providing resources as like, whether it's simulation or at some point, hopefully, NASA will actually have an actual platform to fly on, sort of the best technologies. If everybody starts applying their techniques to a set of identified benchmark problems, then we have something to compare across, and hopefully they're exciting and challenging enough that academia embraces it. As I said, we're publishing a set, the first set in details SciTech 2025, but I'm hoping that we can get more input from other sources that will help us make sure that these benchmark problems are actually representative across the community needs. And that is something that I can definitely say NASA would support. So
May
that's
I
my
say
kind of
also
2 cents.
something? Okay, go ahead.
Hello, can I say something? Okay, I very much agree with what Irene said. The establish of benchmark of the framework and its effective of AI or machine learning, how they react with sensing, how they react with transition, how you react with control. So if we remove the machine learning, we know how to certify airplane. It has been done for a long time. It's not perfect, but actually it's very, very good. So the new component is the machine learning. And in fact, it's the framework of machine learning and how it reacts with sensing, perceptions, and control. So to certify it, the first thing, like Irene suggests, is we need to have benchmark, have a failed model around those dimensions we're talking about. And then we see whether or not our verification and containment and recovery method can work. So I very much agree with Irene said. Without such a common benchmark, or so including the fail mode and the effectiveness of fall and fail identification and recovery, then it's very, very hard to convince anybody. In fact, that has been a culture of AI, right? If we don't have the ImageNet, then everybody say, "Oh, my CNN or whatever machine learning can identify face the best. Look at my result." So everybody publish their own thing, I wouldn't make much progress just because the effort have this large collection of images. So that we become a benchmark. So I'm very much supporting what Aaron said. Let's work together. Look at the traditional certification method, like Aaron said, what it need to be modified. Personally, I was involved in that. I would say the old certification is very, very process oriented. And the process oriented method, I would say, like Aaron implied, are not good for this fundamental new technology because machine learning is a self-modifying software. Okay, I'm not saying it's self-modifying on the fly, okay? That may be a distant future. But every time you train it, you modify the software. If we use the old process, you need to recertify. Now that is economically undoable. So what I try to say, we have to certify from the containment perspective. I don't want to go into technical detail, but all we try to say is we have to go to an evidence-based approach instead of the old process-based approach. Assume that the software is not going to change. That fundamental assumption and underlying the current DO70XC, that's not going to work for this new technology. Because what needs to work, I have some suggestions. I don't want to talk about that, but what we need to talk about is, I will start from what Irene said. Why the old process-oriented or mainly process-oriented certificate approach is unfit if we want to use learning. Fundamentally, the software keeps changing. Learning is changing. Assume static software rarely get changed. And you know where the module get changed. Wouldn't work in AI. In AI, the modularization unclear. Which layer responsible to do what? Not clear. So what I really try to say is a fundamental research is how to certify AI. To do that, we need to have, through the community effort, we need to understand the fail mode of AI software, actually mean algorithm level, and actually the plain software level. A lot of software is putting on Python. Python is very buggy. All right. Python software would not certifiable at all. And the numerical package in Python is also poor. So we're really talking about the software implementation level and the algorithm level. So we really need a new certification perspective. Now, how to do it, I have my own suggestion, but I don't want to talk about it today. But I would say we need to get together. I think Kevin is absolutely right. If we do not move towards a certifiable machine learning-based system, then it will remain academic research forever until something suddenly happens. All right, so I wouldn't say it won't happen, but certainly it's not a managed process like 6 years or 10 years or something like that, or even 3 years. So if we want to take a managed process, then we need to put the certificate issue. So, for example, Kevin talked about repeatedly, they use learning in parts of their software. They have some idea to get it certified. But he has more questions about the challenges than the answers he has. So people from Boeing, from Lockheed, should tell us their concern. And then we'll work to benchmark, and then the researchers can create different methods, see which way work out. And then, like Ari said, we can move up. Without a common framework or benchmark, we are not going to make much difference. To begin, we need to have a Zoom meeting just on that topic, proposed by Irene and Kevin. AI who can well we can spend another 2 years to consolidate technology and then show we can move towards meeting new evidence-based certification also. So I think we should start with a meeting just on that topic. It's a big topic. It's not an easy topic.
We still have another presentation on the outreach efforts. Not sure, but now the discussion is just good. Not sure if we continue the discussion or hear the outreach presentation before we.
So it's almost 2 o'clock our time. So why don't we go ahead? So why don't we do outreach?
Okay, Stephanie, go ahead.
And let me go share my screen. Can you hear me and are you seeing my screen?
Yes.
Excellent. So today, Joe Muskin and I are going to talk about outreach and how we're engaging the next generation. And so while we're going to talk about specific things that we're doing, really the whole lens of this and everything we're doing is to address a pipeline, right? So we're looking at pre-college students, undergraduate students, and graduate students to kind of build different level of expertise and technical skills as they go through. So for the undergraduate education piece, we have had 3 REU students for undergraduate research experiences. Alonzo Arostegui was an aerospace major from UIUC who did an REU in the summer of 23. We had Kennedy Burchell, who was from our department in our university, who did an academic year REU. So she worked in the fall and the spring. Fall 23, spring 24. And then this past summer, we had Caitlin Rovig, who's a mechanical engineering student from the University of Nevada, Reno. And so they worked on various different topics and they were advised by 6 different graduate student mentors. And you'll see that some common highlights is they all presented at professional conferences, poster sessions, presentations. They participated and had opportunities at least a couple a week for professional development opportunities and workshops to kind of build technical skills, but also to build professional presence. And then we have started, as we're kind of iterating on this, involving the REU students and actually mentoring pre-college students. And so here, Caitlin was in the clean room here and helping some high school students, a diverse group of high school students, kind of pattern and etch silicon wafers. And so we're hoping also to build in not only the comfort level with research and thinking about grad studies, but also maybe mentoring, right, for if they joined a research group. And so our future plans for this year are to get 2 more undergraduate students for REUs from various populations. And we've already collected over 20 applications and over half of them are kind of in these underrepresented group demographics. So I don't think we'll have any trouble finding more REUs. As far as pre-college involvement, there is pre-college involvement happening at University of Nevada, Reno with Jessica Peterson. And here we see this video. So at the Aviation Day, Girls on Aviation Day and the STEM Discovery Zone, students can wear these augmented reality headsets. And Jessica actually made this video with NASA. They can feel what it's like to kind of put on the gear to be in a flight. And the reach of these events was great, nearly 8,000 students. And currently she's working with the University of Nevada, Reno, Upward Bound students. And in the spring, she'll be rolling out some presentations and educational content for those students. Corey Bennett at NC North Carolina A&T is working with slightly younger students. So generally grade school, middle school, and he's had a great reach presenting robotics at 2 different academies. I think robotics kind of builds that same technical skill set and maybe has some better safety control than drones or blades that are spinning around. And so it's really kind of building those skills needed to get like keep going further in their education and hopefully wind up in a STEM college program working with this content later. And so I'm going to hand it over to Joe, and he'll continue to talk about our pre-college involvement at U of I.
Hello, I'm Joe Muskin. One of the things that we want to do is have some sustainability to the program, and so we're developing a drone module where students design and build a drone and then go ahead and fly it. We started this work last year and continued it again this year. Last year we made a lot of success and discovered that we still had a couple of bugs to work out. So we brought back some pre-college students to test it, and here you can see they actually built and got their drones to fly. One of the kind of the nice things I like about this video is we took the students into the lab, the drone lab there on campus, and saw the net and the flooring so that the drones don't crash and destroy themselves. And so we wanted to recreate that in kind of a portable setting. And so we got one of these pop-up tents with some netting, and then a mattress pad for the bottom. And so that's a pretty inexpensive place to fly. And the nice thing is it's portable, and so we can use this all over the place. We had last year and this year, we had some students testing this this out. We had a group of students work pretty intensely for the summer, where they gained a lot of kind of research skills. We had a total of, go back a slide still. We still had about 10 undergrad students who are definitely going on to college and likely going into engineering and maybe even this field, you know, drones and aviation. And so we gave them a little bit of experience while they piloted a lot of stuff for us. And these students actually presented at an Illinois conference. So they put together their materials last year and presented. They did the same thing this year and presented with the different students. And so that's worked out real well. And then we piloted this. And so now you can go on. We've piloted this, and you'll notice that this slide is actually a different format. That's because we piloted this at some schools in Chicago that serve a lot of Black and Hispanic students, and they were so excited about this that they actually presented this program to their administration. And this is a slide from that presentation. And so I wanted to just capture that slide. You can see the students, they had kind of a 6-week-long camp where these high school, where these middle school kids worked on these drones and actually got drones to fly kind of after school. And we're going to continue that again this year. We're going to do that at a few different places. The next slide shows it at Campus Middle School for Girls, where we also did it. And here you can see some of the people from the university lab there came in and helped with this. The students designed and built their drones, and so that was kind of successful. And we're going to continue doing this as we're kind of finishing up this module and testing it. We're getting really close, I think, to being able to publish this and disseminate this widely. We're going to go again back to Campus Middle School. We're going to do it at our summer camp here at the University of Illinois. The Chicago group is going to continue to do it. And then there's a fourth group. There's a local group here in Champaign that works with underrepresented minority students pretty extensively after school, called DREAM. And DREAM is going to also pilot this for us. And I think after we get those 4 groups and the feedback, I think we'll be ready to publish this and disseminate it So we're looking forward to doing that. So go ahead and next slide. So this whole module, the students are going to learn CAD. They'll design a frame. They'll 3D print the frame. They'll assemble the drone and test it. And so I think we have kind of everything worked out. The nice thing about this, they're going to be working in groups, kind of seeing that engineering is this collaborative process, especially now. Kind of a lot of pre-college students have this idea of engineering being this thing that is really for kind of nerdy kids, and you don't get to interact, and it's kind of all by yourself. And so showing them that real engineering actually is very collaborative helps bring in a lot of pre-college students who might not be as interested in engineering from their incorrect perceptions of what it is. One of the nice things about this is that each group's design is different, and that's kind of important because it tells the students that they're engineers and they're successful when their design works. Even when seeing other people, it's not so cookie cutter, that they see that theirs works, and so they were the engineers and they got that thing to work. So we think those are kind of important components of this to really try and bring in more students. And so go ahead and go to the next slide. And so that's the pre-college, and we're also working with the grad students. The grad students were really working on mentoring and leadership development. And so they're working closely with the REUs. In fact, they're leading the REU's research, and it gives them a chance to develop their mentoring skills. You know, someday they're going to either be working in industry or they'll be in academia, and they'll have their own employees or their own students. And so they need to be able to develop these skills. And this is a nice way to do that. And we do scaffold it a bit. We give them a mentoring agreement that they and their mentee fill out at the beginning that goes over sorts of things, expectations. And so it kind of tries to get everybody on the same page. It helps the mentors learn where their mentees are at and to be a more effective mentor going forward. And so we're kind of scaffolding that experience for the mentors as well, so that they'll become better mentors. We also have the grad students involved in the pre-college development. You can see over there we're in the lab, and they're working with that group of students who came in and tested things pretty extensively for us and developed a lot of things for us. And then at the end, we collect feedback from the mentees and give this back to the mentors so that they can kind of see where their weaknesses are, what they need to think about for next time they're dealing with mentees and stuff like that. So let's go to the next slide. And this is how we're really addressing this pipeline. We're getting the pre-college students, getting a lot of students who might not be thinking about engineering, trying to get them interested and engaged in engineering. We're working with undergrads where we're getting them ready for grad school and to think about going on in their education. And then we're working with the graduate students in developing their mentoring skills. And so that's the educational program kind of in a nutshell. So I'm going to turn it back to Stephanie and myself. Any questions?
Thanks, John. It was excellent. Thanks.
You guys are doing a lot of very nice work.
Thank you.
Thank you.
No questions, I guess, is a good thing, right? It means we explain things fairly well.
All right, thank you, Greg. So are we done with day 2, or we still have discussion? Irene, what's the plan?
That's my questions. Any further discussion from the advisory board? Any follow-throughs?
Not for me. I think I had my discussion, I think.
see, who else do we have? Lena or Richard?
I don't think I have any other discussion. One thing, as you all know, I missed the Thrust 2 presentations. Thank you for posting the videos. I'm actually not able to access them when I click in the chat. It says I'm not part of the organization or something like that. It would be useful if I could get access to those, just so I could look through what got presented yesterday in the session I missed.
Sure, Sheng will make it available.
Okay. Yeah,
Yep,
the error I get, Sheng, is only org members have access to the meeting recap when I click on that link where the videos are.
Yep.
Oh, Richard, that's what you're talking about. So actually we have transferred those videos out of this Teams because we realized there were access issues with recording inside here. So we'll make sure to forward you the latest link where you can access these recordings as well as the transcripts, the chat we have organized.
Great, thank you.
No problem.
Sheng, make it
Sheng.
accessible to all the committee.
Yeah, the advisory board, that would be great. That way I don't have to deal with downloading, uploading.
Yeah, that'd be useful.
Would you mind sending that to my Illinois email address? ky@illinois.edu. I can't access these links at Boeing. Yeah. Thank you.
Sure, noted. So what I will do with Duo on our side is we're going to send you this organized folder with recording, transcripts, chat, and also we have one for the slides of the presentations in one link so that you can access everything. You don't have to log back to the Teams. So this is designed to make sure the maximum possible convenience for everybody.
The slides are on IB8 website, which we thought they should be available for public dissemination. But the recordings and the chat and transcripts will share with you kind of for your individual access.
Excellent.
Thank you.
All right. Thank you. Then the plan for tomorrow is the advisory committee will meet at 10 o'clock Central on advisory committee only Teams link. And then when we finish, we will transfer to the general Teams for the brief out and for the discussion.
Thank you, Irene. So look
right.
forward to tomorrow. Thank you very much for everyone's attendance, participation.
Yeah, thanks everyone. I really enjoyed all the briefings today. Very, very good. Thank you.
Thank you. See you tomorrow.
Thank you from my side too. These were excellent work and very interesting.
Yep. Thank you, everybody. Have a good evening.